And that's where they say Eisenhower made a deal with these aliens.
I think we're getting very close to rediscovering some of the things that our ancient ancestors were up to.
Antarctica has been a source of both scientific intrigue and speculative conspiracy theories. With its harsh climate, vast icy landscapes, and mysterious history, the frozen continent at the bottom of the Earth has captivated explorers, scientists, and conspiracy theorists alike. But recently, the White Continent has attracted attention from an unlikely source, Elon Musk. Known for his revolutionary ideas in space travel, electric cars, and artificial intelligence, Musk has now thrust himself into the heart of one of the most controversial topics in modern history, the alleged alien cover-up in Antarctica.
You can really go down a deep rabbit hole if you read about ice ages.
Join us as we dig deep into the mystery of Antarctica and Musk's revelations about what may be happening beneath the sheet ice. The idea of a vast southern landmass existed long before Antarctica was discovered. Ancient Greek philosophers speculated about the existence of a terra australis incognita, an unknown southern land that was thought to balance the land masses in the northern hemisphere. This notion persisted through the Middle Ages and into the Age of Exploration, even as explorers charted the southern oceans without finding evidence of such a place. The mystery of whether a great southern continent truly existed became one of the driving forces for explorers venturing into the polar regions. One of the earliest references to this mythical southern land can be found in the works of Ptolemy, the Greco-Roman geographer, who suggested that there must be land in the southern hemisphere to counterbalance the weight of the continents in the north. This theory, though speculative, held sway for centuries and inspired cartographers to include vast, uncharted lands at the bottom of their maps. The mystery of the Terra Australis gave birth to many legends and fantastical stories, which only added to the allure of the unknown. However, the true discovery of Antarctica did not come until the 19th century, when European explorers began venturing into the treacherous southern waters in search of new trade routes and uncharted territories. In 1820, several expeditions, including those led by the Russian explorer Fabian Gottlieb von Bellingshausen and the British naval officer Edward Bransfield, reported sightings of the icy landmass. Over the next few decades, explorers like James Clark Ross and Charles Wilkes mapped parts of the Antarctic coastline, confirming that the Terra Australis was not a myth, but a real and formidable landmass. But even as explorers began to chart the edges of Antarctica, the continent's interior remained largely unknown. The forbidding climate and impenetrable ice fields made exploration incredibly difficult, reinforcing the idea that Antarctica was a place of mystery and danger. Early expeditions were often perilous, with explorers facing extreme cold, blizzards, and treacherous conditions. The harrowing tales of survival, such as those of Ernest Shackleton's ill-fated endurance expedition, only heightened the sense of Antarctica as a land of extremes, where the line between life and death was precariously thin. While the early explorers sought to chart the unknown, the 20th century brought a new wave of interest in Antarctica, driven by scientific curiosity. The continent's isolation and unique environment made it a natural laboratory for studying the Earth's climate, geology, and biology. For instance, the discovery of the ozone hole in the 1980s highlighted the importance of Antarctica in understanding global environmental processes. Moreover, the frozen continent holds within its ice cores a record of Earth's climate history, offering invaluable insights into past climate change and future trends. But Antarctica's scientific significance extends beyond Earth's climate. The continent's barren, icy surface has often been compared to the conditions on Mars, leading scientists to use Antarctica as a testing ground for technologies that might one day be employed in the exploration of other planets. The discovery of microbial life in subglacial lakes beneath the Antarctic ice sheet has raised tantalizing questions about the potential for life in extreme environments. both on Earth and elsewhere in the solar system. Adding to the scientific allure of Antarctica is the fact that much of the continent remains unexplored. Beneath the ice lies a hidden world of subglacial lakes, rivers, and mountains, including the mysterious Gamburtsev Mountains, which are completely buried under the ice sheet. These hidden features, along with the prospect of discovering new forms of life or ancient geological formations, continue to fuel the fascination with Antarctica as a frontier of scientific discovery. As the 21st century progresses, Antarctica remains a place of great scientific interest and human fascination. Climate change is altering the continent's ice sheets and ecosystems, raising questions about the future of this fragile environment and its role in regulating global climate. At the same time, technological advancements are allowing scientists to explore previously inaccessible regions of the continent, uncovering new mysteries and deepening our understanding of this unique part of the planet. However, despite these advances, Antarctica's mystique endures. It is a place where the unknown still looms large, where the boundaries of human knowledge are continually being pushed, and where the ancient and the futuristic collide. Whether through scientific discoveries, speculative theories, or tales of adventure and survival, Antarctica continues to capture the imagination, a frozen frontier that remains as enigmatic today as it was to the ancient philosophers who first dreamed of a southern land at the edge of the world. Thus, this continent has long been the subject of rumors and conspiracies. Some believe that Antarctica is home to ancient civilizations hidden beneath miles of ice, while others insist that secret Nazi bases were established there during World War II. But perhaps the most enduring and provocative theory is that of an alien presence. According to this theory, extraterrestrial beings may have used the isolated continent as a base for their activities, and these secrets have been buried under the ice for millennia. Elon Musk is no stranger to space exploration and the idea of extraterrestrial life. His long-stated mission with SpaceX has been to make humanity a multi-planetary species, and he has frequently discussed the possibility of life on other planets. However, few expected him to wade into the murky waters of Antarctic alien conspiracies. In a surprising series of tweets and interviews, Musk began to hint at the possibility that Antarctica was not just an empty, frozen continent. He alluded to things beneath the ice that the public had not been told about. While his statements were often cryptic, they seemed to suggest that he had knowledge of hidden truths that might connect to extraterrestrial life. During a 2023 podcast, Musk dropped a bombshell claiming that there's something ancient and otherworldly down there, and that we are not being told the full story. These comments ignited a media frenzy, with some accusing Musk of fueling conspiracy theories, while others speculated that he might know more than he was letting on. Central to Musk's cryptic revelations is the long-standing theory that Antarctica houses a secret alien base, possibly hidden beneath the ice or buried deep within its mountains. This theory posits that extraterrestrials either crash-landed or intentionally set up operations on the continent thousands of years ago. The harsh and desolate environment of Antarctica would make it the perfect location for extraterrestrials to conduct activities without the interference of humans until recent times. Some versions of the theory suggest that governments, including the United States, are aware of this alien presence and have kept it hidden from the public. Proponents of this idea point to the Hollow Earth belief and the 1946-1947 military operation known as Operation High Jump, led by U.S. Admiral Richard E. Byrd. The Hollow Earth theory, as the name suggests, posits that the Earth is not a solid sphere, but instead contains vast, empty spaces or even entire civilizations within its crust. This idea can be traced back to various ancient cultures and philosophers, including the Greek thinker Anaxagoras and some interpretations of Hindu and Buddhist cosmology. However, the modern version of the Hollow Earth theory became popular in the 17th century with the works of English astronomer Edmund Halley, who proposed that the Earth might consist of concentric spheres, each with its own atmosphere and life forms. As explorers ventured further into Antarctica in the 20th century, the hollow Earth theory became intertwined with the continent. The most well-known figure associated with this idea is Rear Admiral Richard E. Byrd of the United States Navy. Byrd was an American explorer who made several expeditions to Antarctica between 1928 and 1956, including the famous Operation High Jump in 1946-1947, a large-scale military operation in the region. According to his diary, Byrd discovered an entrance to the hollow Earth during one of his expeditions. Byrd's flight over the North Pole led him to enter an inner world populated by advanced beings, sometimes referred to as the Agarthans, who had superior technology and knowledge. Byrd's diary describes lush landscapes, large animal species like mammoths, and flying saucers that accompanied his aircraft. While Byrd's documented history never officially confirmed, this gap in official information has led to the spread of speculative theories. Operation High Jump, in particular, has drawn suspicion from conspiracy theorists who argue that the true objective of the mission was to explore entrances to the hollow Earth and establish a military presence near these hidden regions. The sheer size and scope of the mission, a fleet of ships, aircraft, and thousands of military personnel, raised eyebrows, and many believe that the U.S. government was interested in something far more extraordinary than mapping the frozen wilderness. Another cornerstone of the Antarctic hollow Earth conspiracy revolves around Nazi Germany's alleged interest in the continent. Some theorists claim that the Nazis built secret bases in Antarctica during World War II as part of their occult and scientific explorations. According to these legends, the Nazis were particularly interested in the hollow Earth and may have believed that the inner world housed an ancient, advanced race. The theory asserts that after the defeat of Nazi Germany, some high-ranking officials fled to Antarctica to continue their work. In these underground bases, supposedly constructed beneath the Antarctic ice, the Nazis pursued secret technologies, including UFOs and advanced weaponry, eventually disappearing into the hollow Earth or continuing their research in secrecy. In addition to theories about the hollow Earth, many conspiracies suggest that Antarctica was once home to advanced ancient civilizations. According to these theories, the continent wasn't always covered in ice, but was once a temperate region where highly developed societies lived. This idea is bolstered by the concept of Earth crust displacement, popularized by Charles Hapgood, which suggests that the Earth's crust shifted, moving Antarctica from a more temperate zone to its current polar location. Supporters of this theory often point to the Piri Reis map, a 16th century map created by the Ottoman admiral Piri Reis, which shows a detailed coastline of Antarctica without ice. Believers argue that the map proves ancient civilizations had knowledge of the continent long before its modern discovery, possibly because they lived there. However, historians and cartographers explain that the Piri Reis map likely depicts the South American coastline and not Antarctica at all. The idea of ancient civilizations in Antarctica gained further attention with the popularization of Erich von Däniken's Chariots of the Gods, which speculated that extraterrestrial beings had visited Earth in ancient times, bestowing knowledge upon humans and establishing advanced societies. Proponents of this theory often link Antarctica to the myth of Atlantis, suggesting that the lost city was located on the continent before it froze over. The Atlantis myth, first mentioned by the Greek philosopher Plato, describes a highly advanced civilization that existed thousands of years before being destroyed in a cataclysm. The precise location of Atlantis has been the subject of speculation for centuries, with many theorists proposing various sites across the globe. One such location is Antarctica. Proponents of the Antarctica Atlantis theory argue that before the last ice age, Antarctica was home to the legendary city. They suggest that when the Earth's crust shifted or due to a natural disaster, the continent moved southward, becoming covered in ice and burying the remnants of Atlantis. Supporters of this theory often point to pyramid-like structures supposedly found in satellite imagery of Antarctica as evidence of ancient architectural feats. These pyramid-shaped mountains have fueled speculation about a lost civilization that once thrived on the continent. And Elon Musk's comments have just added fuel to this narrative. If Musk has inside knowledge, perhaps obtained through his connections with NASA or other space agencies, it raises the question of how much the world's governments know and what they may be concealing from the public. While Musk's statements might seem outlandish to some, they coincide with a number of strange discoveries that have been made in Antarctica over the years. In 2017, a team of scientists made headlines when they discovered a massive anomaly beneath the continent's ice, located in the Wilkes Land region. Using satellite data, researchers found what appeared to be a huge object buried beneath the ice, one that some speculated could be the remnants of a meteorite or even a large structure. Conspiracy theorists quickly seized on this finding, claiming it was evidence of an ancient alien craft or base. In addition to the Wilkes Land anomaly, there have been reports of unusual magnetic readings in other parts of Antarctica, suggesting the presence of unknown metallic objects or underground structures. In 2018, a team of scientists discovered a series of strange, rectangular structures beneath the ice, prompting further speculation about the existence of ancient or extraterrestrial technology buried beneath the frozen landscape. These discoveries, combined with Musk's comments, have led many to question whether the scientific community is fully aware of what lies beneath the Antarctic ice, or if they, too, are being kept in the dark. After all, what could drive someone like Elon Musk, a man of science and technology, to make these kinds of statements? Some believe that Musk, with his vested interest in space travel and human colonization of other planets, may genuinely believe that extraterrestrial life has visited Earth and that governments are covering it up. His quest to push humanity to explore beyond Earth could be motivated by a desire to uncover these secrets and share them with the public. Others speculate that Musk might be playing a strategic game. By hinting at the existence of aliens in Antarctica, he could be trying to rally support for SpaceX's long-term goals of space exploration and Mars colonization. If the public begins to believe that aliens have already visited Earth, it could spark a renewed interest in the cosmos and drive more investment and attention toward Musk's space-related ventures. Meanwhile, others think that Musk's comments might be a way of testing the waters, seeing how the public reacts to the idea of extraterrestrial life before revealing any concrete information. If he does indeed have inside knowledge, he may be slowly leaking it in order to avoid shocking the world with an immediate, full-blown revelation. If Elon Musk's cryptic revelations hold any truth, the implications would be staggering. The discovery of an alien presence in Antarctica, or anywhere on Earth, would fundamentally reshape our understanding of humanity's place in the universe. It would also raise serious ethical and political questions. Why have governments kept this information hidden? What would be the consequences of revealing it to the public? Some argue that disclosing the existence of extraterrestrial life could lead to mass panic, while others believe it would usher in a new era of technological and scientific advancement. Musk himself has suggested that the existence of aliens could prompt humanity to accelerate its efforts to become a multiplanetary species, as it would demonstrate that we are not alone in the universe. Additionally, if advanced alien technology has been hidden beneath the ice in Antarctica, it could provide a treasure trove of knowledge for scientists and engineers. Imagine the possibilities: new energy sources, faster-than-light travel, or medical advancements far beyond our current capabilities. In short, Elon Musk's revelations, whether based on concrete knowledge or speculative curiosity, have undoubtedly reignited public interest in Antarctica and the possibility of extraterrestrial life. As more people demand answers, governments and scientific institutions may be pressured to disclose what they know. In recent years, there has been a growing movement for greater transparency on the issue of UFOs and extraterrestrial phenomena. In the United States, the Pentagon has declassified several reports and videos of unidentified aerial phenomena, sparking renewed interest in the topic. Musk's statements may push this movement even further, prompting a new era of disclosure in which hidden truths about Antarctica and the possibility of an alien presence come to light. In the end, whether Musk's revelations are rooted in fact or simply a fascinating theory, they have reignited the public's imagination. As humanity stands on the brink of becoming a spacefaring civilization, the question of whether we are alone in the universe looms larger than ever before. And perhaps, as Musk suggests, the answers to that question lie not in the distant stars, but right here on Earth, buried beneath the ice of Antarctica. While waiting for the stunning discoveries in the White Continent, let's take a quick look at the Musk Mars mission. Elon Musk's obsession with Mars is not without reason. The red planet, though cold and barren, offers some of the most promising conditions for potential colonization within our solar system. Its similarities to Earth, particularly its day-night cycle, a Martian day is just over 24 hours, make it more feasible for human habitation compared to other celestial bodies like Venus or the Moon. Mars also has polar ice caps that can be mined for water, and its atmosphere, though thin and composed mostly of carbon dioxide, can be a resource for producing oxygen and rocket fuel. However, Musk's Mars mission is not just about scientific discovery or economic opportunities, it is about ensuring the long-term survival of humanity. Musk has repeatedly warned that life on Earth is fragile, susceptible to existential risks like asteroid impacts, nuclear war, or climate change. Colonizing Mars would provide humanity with a backup in case of a catastrophic event on Earth. In Musk's words, it's about preserving the light of consciousness. At the heart of the Mars mission is SpaceX's Starship, a fully reusable spacecraft designed for deep space travel. Starship is a marvel of engineering, capable of carrying up to 100 passengers or 100 metric tons of cargo on interplanetary missions. Standing at 120 meters tall, the two-stage rocket consists of a super heavy booster and the Starship spacecraft. The booster provides the immense thrust required to break free of Earth's gravity, while Starship, after reaching space, serves as the cruise vessel for the journey to Mars. One of the most significant innovations in SpaceX's mission is reusability. Traditionally, rockets are used once and discarded, making space travel prohibitively expensive. However, SpaceX has pioneered the development of reusable rockets, dramatically lowering the cost of launches. Reusability allows Musk's vision of making space travel affordable for non-billionaires. The aim is to eventually reduce the cost of a one-way trip to Mars to around $200,000 per person. Another technological breakthrough is in situ resource utilization, also known as ISRU. SpaceX plans to use the resources available on Mars to sustain life and produce fuel. For example, the carbon dioxide in Mars' atmosphere can be combined with water from the planet's ice caps to produce methane and oxygen, a process known as the Sabine reaction. Methane can be used as rocket fuel for the return trip to Earth, making missions more self-sustaining. The Starship also features an advanced heat shield to protect the craft during re-entry into planetary atmospheres, whether returning to Earth or landing on Mars. Moreover, SpaceX has developed the Raptor engine, a highly efficient and powerful engine fueled by methane and liquid oxygen, specifically designed for deep space missions. Of course, Musk's Mars mission will likely unfold in several stages, each more ambitious than the last. Before launching crewed missions to Mars, SpaceX is focused on perfecting Starship through a series of test flights. SpaceX has already performed multiple high-altitude tests of Starship, with several successful landings. The next step involves flying Starship to the Moon as part of NASA's Artemis program, which aims to return humans to the lunar surface by 2025. This Moon mission will serve as a proving ground for Starship's capabilities and provide valuable insights into long-duration space travel. Before humans set foot on Mars, SpaceX plans to send several unmanned starships to the planet. These missions will carry cargo, including supplies, habitats, and equipment for ISRO. Establishing infrastructure on Mars beforehand is critical for the success of future crewed missions. The first manned mission to Mars is tentatively scheduled for the late 2020s. This initial mission will likely consist of a small crew tasked with setting up a base and testing life support systems. Over time, the missions will grow in size and complexity, eventually leading to the establishment of a permanent settlement. Musk's ultimate goal is to build a self-sustaining city on Mars, with a population of 1 million people by the end of the century. This colony would not only survive but thrive, with its economy, agriculture, and even manufacturing capabilities. SpaceX envisions the construction of domed habitats filled with air and vegetation, powered by solar energy and protected from radiation by thick walls made from Martian regolith. Having said that, Elon Musk, through SpaceX, has undoubtedly become the poster child of humanity's race to Mars, dominating headlines with his bold proclamations of colonization and interplanetary expansion. But Musk is not the only player in the race to the red planet. Governments, private companies, and even international coalitions are all vying for their place in the history books, each with their own strategies, technologies, and visions for what a human future on Mars might look like. While SpaceX is spearheading the conversation, several other entities are quietly and not so quietly competing in this new space race. Before Musk became synonymous with Mars, NASA had been laying the groundwork for Martian exploration. Decades of robotic missions, including the famous Curiosity and Perseverance rovers, have slowly pieced together critical data about Mars's environment, atmosphere, and potential for sustaining life. NASA's Artemis program, which aims to return humans to the Moon by the mid-2020s, is widely seen as a stepping stone for eventual human missions to Mars. However, NASA's plan for Mars is more measured compared to Musk's audacious goals. While Musk envisions millions living on Mars within decades, NASA is more focused on developing a sustainable presence, one that builds up gradually over time. The agency's current timeline envisions sending humans to Mars in the 2030s. To that end, NASA is working on a variety of technological solutions for space travel, habitat construction, and life support systems. NASA's SLS, or Space Launch System, is the centerpiece of their Mars plan, providing the heavy lift capability required to transport astronauts and cargo to the Red Planet. Additionally, the Orion spacecraft will carry the astronauts on their multi-month journey to Mars. NASA's collaborative partnerships with private companies like SpaceX and Lockheed Martin demonstrate that they recognize the need for cooperation rather than competition in achieving such an ambitious goal. Besides NASA, China's rapid ascent as a space power has become impossible to ignore. Through its space agency, the China National Space Administration, or CNSA, the country has consistently demonstrated its capability in space exploration, from landing rovers on the Moon and Mars to constructing its own space station, Tiangong. In May 2021, China became the second country ever to successfully land a rover on Mars with its Tianwen-1 mission. China's Mars ambitions are growing, and they are not just symbolic. The country's long-term plan envisions sending humans to Mars by the 2030s, a timeline that closely mirrors NASA's. China has also been developing the technology necessary for such missions, including heavy-lift rockets like the Long March 9, which will likely be critical for manned missions to Mars. Moreover, China's space program operates with a high level of government backing and long-term strategic planning. Unlike NASA, which relies on fluctuating political support and budgets, CNSA benefits from a more centralized and sustained funding model. This allows China to develop technologies and programs over decades, positioning the country as a serious contender in the race to Mars. Their space diplomacy, which often includes partnerships with other countries, signals that China is not only aiming for Mars, but also looking to lead in international space cooperation. On the other hand, the European Space Agency, or ESA, also has long been a partner in various international space missions and continues to play a key role in Mars exploration. While the ESA may not have the same solo ambitions as NASA or SpaceX, it is heavily involved in collaborative missions aimed at understanding Mars and laying the groundwork for human exploration. The ESA's ExoMars mission, in partnership with Roscosmos, aims to drill beneath the Martian surface to search for signs of life. The ExoMars rover, set to launch in the coming years, is designed to complement NASA's efforts in unraveling Mars mysteries. Moreover, the ESA is developing the technology to contribute to international manned missions to Mars, from life support systems to transportation modules. Additionally, the ESA has its eye on Mars sample return missions, a critical stepping stone to future human exploration. These missions will involve sending spacecraft to Mars, collecting samples, and bringing them back to Earth for detailed analysis. Such efforts are seen as crucial for understanding the Martian environment and assessing its potential habitability. Elsewhere, Russia, through its space agency Roscosmos, has been a major player in space exploration since the early days of the space race. While its space program has faced significant challenges in recent years, including funding issues and increasing competition, Russia still retains considerable expertise and ambition. Roscosmos has partnered with ESA on the ExoMars mission and is reportedly working on developing its own crewed Mars mission. Russia's historical contributions to space travel, particularly its success in launching humans into space, are not to be underestimated. However, it remains to be seen whether the country can overcome its current hurdles and reassert itself as a leading force in the race to Mars. Last, Elon Musk's most notable competitor in the private sector is Jeff Bezos, founder of Blue Origin. While Bezos has largely focused on lunar exploration, with plans to build a sustainable human presence on the Moon, he has expressed interest in Mars as well. In Bezos's vision, the Moon serves as a launching point for deeper space exploration, including missions to Mars. Blue Origin's New Glenn rocket, currently in development, is seen as a direct competitor to SpaceX's Starship and NASA's SLS. If successful, New Glenn could provide the capability to send humans and cargo to Mars. Bezos has also spoken of the need to build space habitats that would allow humanity to live and thrive beyond Earth, a vision that aligns with long-term colonization of both the Moon and Mars. Though Bezos's plans for Mars are less developed than Musk's, Blue Origin's growing presence in space exploration means it could become a formidable player in the Martian race in the years to come. And of course, one of the most promising aspects of the Mars race is the potential for international cooperation. As space becomes increasingly accessible, more countries are establishing their own space programs, with varying levels of success. Countries like India and the United Arab Emirates have already demonstrated their capability in space exploration with successful Mars missions. In 2014, India's Mangalyaan mission became the first Asian spacecraft to enter Mars orbit, while the UAE's Hope probe successfully reached Mars in 2021. These countries, along with others, are showing that the future of Mars exploration may not belong solely to any one country or corporation. International partnerships, like the ones already seen between NASA, ESA, and CNSA, could prove critical in overcoming the technological, financial, and logistical challenges of reaching Mars. A collaborative approach might also be the most sustainable way to ensure humanity's long-term survival on another planet. In short, Elon Musk and SpaceX may be the most visible champions of the race to Mars, but they are far from alone. Governments, private companies, and international coalitions are all working toward the same goal, albeit with different strategies and timelines. As the race heats up, it is becoming increasingly clear that the journey to Mars will not be a solitary endeavor. It will be a global one. The competition may drive innovation, but collaboration will likely determine whether humanity succeeds in becoming a multi-planetary species. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
About quark gluon plasma.
That's bad. That's bad for physics. With the cosmic microwave background, the leftover radiation from the Big Bang.
But you would like something.
NASA has been at the forefront of space exploration and scientific discovery for decades. Its relentless pursuit of knowledge has unveiled a series of discoveries that have profoundly altered our understanding of the universe. From distant galaxies and black holes to the early moments after the Big Bang, NASA's missions have expanded the horizons of human knowledge, challenging existing paradigms and fostering new theories. Join us in today's episode as we dig deep into the most significant discoveries that have reshaped our comprehension of the cosmos. Number 1. The cosmic microwave background radiation, the afterglow of creation. One of NASA's most significant contributions to cosmology is the discovery and mapping of the CMB, for cosmic microwave background radiation. The CMB is the faint afterglow of the Big Bang, the primordial explosion that gave birth to the universe approximately 13.8 billion years ago. This discovery provided critical evidence supporting the Big Bang theory, fundamentally altering our understanding of the universe's origins. The CMB was first detected by accident in 1965 by Arno Penzias and Robert Wilson, who won the Nobel Prize in Physics for their work. However, it was NASA's Cosmic Background Explorer, COBE, satellite, launched in 1989, that provided the first detailed map of the CMB. COBE's data confirmed that the CMB was almost perfectly uniform across the sky, with tiny fluctuations that represented the seeds of all the current structures in the universe, such as galaxies and clusters of galaxies. These tiny fluctuations in the CMB provided crucial insights into the early universe's conditions, helping to refine the Big Bang theory and leading to a better understanding of the universe's age, composition, and development. The COBE mission was followed by the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, both of which provided even more detailed measurements of the CMB. These missions allowed scientists to determine that the universe is composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy, a mysterious force driving the universe's accelerated expansion. The discovery and study of the CMB have been foundational in cosmology, providing a baby picture of the universe that has shaped our understanding of everything from the nature of matter and energy to the ultimate fate of the cosmos. Number 2. The accelerating expansion of the universe, unveiling dark energy. In the late 1990s, one of the most groundbreaking discoveries in astronomy was made using data from NASA's Hubble Space Telescope. Scientists found that the expansion of the universe is not slowing down, as previously thought, but is actually accelerating. This discovery was a complete surprise and led to the introduction of the concept of dark energy, a mysterious force that permeates all of space and is driving the universe's accelerated expansion. The discovery was made by observing distant Type Ia supernovae, which are exploding stars that can be used as standard candles to measure distances in the universe. By comparing the brightness of these supernovae at different distances, scientists found that distant galaxies were moving away from us faster than nearby ones, indicating that the universe's expansion rate was increasing over time. The implications of this discovery are profound. Dark energy, which is believed to make up about 68% of the universe, remains one of the biggest mysteries in modern physics. Its discovery has led to a fundamental shift in our understanding of the universe, suggesting that the cosmos could continue expanding forever, potentially leading to a big freeze where galaxies drift apart, stars burn out, and the universe becomes a cold, dark place. NASA continues to study dark energy through various missions, including the upcoming Nancy Grace Roman Space Telescope, which aims to explore the nature of dark energy by measuring the distribution of galaxies across cosmic time. The discovery of dark energy is a testament to the unexpected ways the universe continues to surprise us, challenging our theories and pushing the boundaries of our knowledge. Number 3. The discovery of exoplanets, expanding the search for life. One of the most exciting and transformative discoveries made by NASA in recent decades is the detection of exoplanets, planets orbiting stars outside our solar system. This search was revolutionized by NASA's Kepler Space Telescope, launched in 2009, which was designed to monitor over 150,000 stars in a small patch of the Milky Way galaxy. Kepler's mission was to look for tiny dips in a star's brightness that occur when a planet passes in front of it, a method known as the transit method. Kepler's results were astonishing. The telescope discovered over 2,600 confirmed exoplanets, with thousands more candidates awaiting confirmation. These discoveries revealed that planets are not rare, but are common throughout the galaxy, with estimates suggesting that there are more planets than stars in the Milky Way. Among these exoplanets, several have been found in the habitable zone of their stars, the region where conditions might be right for liquid water to exist on a planet's surface, which is considered a key ingredient for life. One of the most famous of these is Kepler 186, an Earth-sized planet located in the habitable zone of its star. This discovery has profound implications for the search for extraterrestrial life, suggesting that there may be billions of potentially habitable worlds in our galaxy alone. The discovery of exoplanets has opened up a new field of astronomy, with NASA continuing to lead the search for life beyond our solar system. The Transiting Exoplanet Survey satellite, also known as TESS, launched in 2018, is continuing Kepler's work by surveying the entire sky for exoplanets. Meanwhile, the James Webb Space Telescope, JWST, launched in 2021, is poised to study the atmospheres of these distant worlds in unprecedented detail, searching for signs of life. The discovery of exoplanets has fundamentally changed our understanding of the universe, revealing that our solar system is just one of countless planetary systems scattered throughout the galaxy. It has also reignited the age-old question: are we alone in the universe? NASA's ongoing search for exoplanets and the conditions for life continues to bring us closer to answering this question. Number 4. The observation of gravitational waves, a new window into the universe. In 2015, scientists made the first direct observation of gravitational waves, ripples in the fabric of space-time caused by violent cosmic events, such as the collision of black holes. This discovery, which confirmed a major prediction of Albert Einstein's theory of general relativity, was made possible by the Laser Interferometer Gravitational Wave Observatory, or LIGO, a project with significant contributions from NASA. Gravitational waves were first predicted by Einstein in 1915 as part of his theory of general relativity, which describes gravity as the warping of space and time by massive objects. However, detecting these waves proved to be an enormous challenge due to their incredibly faint nature. LIGO, which consists of 2 facilities in the United States, was designed to detect these minuscule ripples by measuring the tiny distortions they cause as they pass through Earth. The first detection of gravitational waves came from the merger of two black holes, each about 30 times the mass of the Sun, located over 1 billion light-years away. This event was named GWW-15914 and marked the beginning of a new era in astronomy, gravitational wave astronomy. The ability to detect and study gravitational waves has opened up a completely new way of observing the universe. Unlike light, gravitational waves are not easily absorbed or scattered, allowing them to carry information about the most violent and energetic events in the cosmos, such as black hole mergers, neutron-star collisions, and even events from the early universe. Since the first detection, LIGO, along with its European counterpart Virgo, has detected dozens of gravitational wave events, providing new insights into the nature of black holes, the structure of neutron stars, and the behavior of matter under extreme conditions. These observations have confirmed that black holes are common throughout the universe and have provided a new way to test the limits of Einstein's theory. Looking ahead, NASA is collaborating on LISA for the Laser Interferometer Space Antenna, a space-based gravitational wave detector that will be sensitive to a different range of gravitational waves than LIGO, potentially revealing new physics and shedding light on the most mysterious phenomena in the universe. Number 5. The exploration of Mars. Searching for life on the red planet. NASA's exploration of Mars has been one of its most enduring and scientifically rewarding endeavors. Since the 1960s, NASA has sent a series of missions to Mars, each more sophisticated than the last, culminating in the recent Mars rovers, such as Curiosity and Perseverance, which have transformed our understanding of the red planet and its potential to host life. One of the most groundbreaking discoveries on Mars came from the Curiosity rover, which landed in Gale Crater in 2012. Curiosity found evidence that Mars once had conditions suitable for life, including ancient riverbeds, lakes, and the presence of key chemical ingredients for life, such as carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Curiosity also detected complex organic molecules in Martian soil, which, while not proof of life, are the building blocks of life as we know it. The Perseverance rover, which landed in Jezero Crater in 2021, is continuing this search for life. Jezero Crater was chosen as the landing site because it is believed to have once been a lake, with river deltas that could have preserved signs of ancient microbial life. Perseverance is equipped with advanced scientific instruments to analyze rocks and soil, searching for biosignatures, chemical or physical signs of past life. One of Perseverance's most ambitious goals is to collect samples of Martian rock and soil that will be returned to Earth by a future mission. This will allow scientists to study Martian material in unprecedented detail, potentially providing the first direct evidence of life beyond Earth. NASA's Mars exploration program has not only provided evidence that Mars was once habitable, but it has also laid the groundwork for future human exploration. For example, the discovery of water ice on Mars suggests that future astronauts could extract water for drinking and producing oxygen and rocket fuel, making long-term human missions to Mars feasible. As NASA prepares for the next steps in Mars exploration, including the potential human exploration of Mars in the 2030s, the discoveries made by missions like Curiosity and Perseverance will continue to be a vital foundation for our understanding of the red planet and its potential to support life. Number 6. The structure of the Milky Way. For centuries, the true shape and extent of the Milky Way remained elusive due to our position within it. However, through the use of advanced telescopes and space missions, NASA has unveiled the intricate details of the galaxy's architecture. The Milky Way is a barred spiral galaxy, characterized by a central bar-shaped region of stars and a disk composed of several spiral arms. These spiral arms, filled with gas, dust, and young stars, wind out from the central bulge, which houses older stars and a supermassive black hole known as Sagittarius A. The galaxy's disk is relatively thin, but it extends for about 100,000 light-years across, with the Sun located about 26,000 light-years from the galactic center, nestled in the Orion Arm. One of the most significant breakthroughs in mapping the Milky Way came from the NASA-led Cosmic Background Explorer, or COBE, and later, the Spitzer Space Telescope. COBE helped confirm the Milky Way's spiral structure by detecting the distribution of stars and dust in infrared light, which penetrates the dense interstellar dust that obscures visible light. Spitzer further refined this view, revealing the intricate details of the galaxy's arms and confirming the presence of the central bar. In addition, NASA's WMAP and the European Space Agency's Gaia mission have provided crucial data about the Milky Way's shape and size. Gaia, in particular, has mapped the positions and motions of over 1 billion stars, giving astronomers an unprecedented 3D view of the galaxy. This data has helped confirm that the Milky Way is not a simple disk, but has a warped shape, likely caused by interactions with neighboring galaxies, such as the Sagittarius Dwarf Galaxy. Moreover, NASA's Fermi Gamma Ray Space Telescope has uncovered evidence of massive bubbles of high-energy radiation extending above and below the Milky Way's disk. These Fermi bubbles are thought to be remnants of an energetic event in the galaxy's past, possibly linked to activity from Sagittarius A. NASA's efforts to map and understand the structure of the Milky Way have not only expanded our knowledge of our galaxy, but have also provided insights into the processes that shape galaxies across the universe. This research continues to evolve, offering new glimpses into the dynamic and ever-changing nature of the Milky Way. Number 7. The exploration of the outer solar system. NASA's Voyager exploration of the outer solar system represents one of the most ambitious and successful endeavors in the history of space exploration. Launched in 1977, Voyager 1 and Voyager 2 were initially designed to take advantage of a rare planetary alignment that allowed them to visit the outer planets, Jupiter, Saturn, Uranus, and Neptune, using gravity assists to propel them from one destination to the next. This grand tour of the solar system provided humanity with its first close-up views of these distant worlds, fundamentally changing our understanding of the outer planets and their moons. Voyager 1 was the first of the 2 spacecraft to launch and quickly became the first human-made object to fly by Jupiter in 1979. The data it sent back revealed the planet's turbulent atmosphere, with its great red spot, a massive storm larger than Earth, and its complex system of moons. Particularly significant was the discovery of active volcanoes on Io, one of Jupiter's moons, making it the first body beyond Earth known to be volcanically active. Voyager 1 then proceeded to Saturn in 1980, where it captured detailed images of the planet's rings and discovered new moons. It also provided a closer look at Titan, Saturn's largest moon, revealing its thick atmosphere, which scientists believe might harbor conditions similar to early Earth. Voyager 2 followed a similar path, but went on to achieve what no other spacecraft has done. It visited Uranus in 1986 and Neptune in 1989. The flyby of Uranus uncovered a magnetic field tilted at a bizarre angle and 11 new moons. Voyager 2's encounter with Neptune provided the first images of the planet's dynamic atmosphere, including the Great Dark Spot, a massive storm similar to Jupiter's Great Red Spot, and the discovery of geysers on Triton, Neptune's largest moon. After completing their primary missions, both Voyager spacecraft continued on their paths out of the solar system, with Voyager 1 becoming the first spacecraft to enter interstellar space in 2012, followed by Voyager 2 in 2018. As of 2024, Voyager 1 is about 15 billion miles from Earth, and Voyager 2 is around 13 billion miles. These distances are vast, but the twins still send data back to Earth by using their onboard instruments and radio communication systems. The signals they send take over 20 hours to reach Earth, traveling at the speed of light. Despite their distance, the spacecraft continue to transmit valuable scientific information about the space environment they encounter as they journey through the outer reaches of the solar system and into interstellar space. The data they send back is helping scientists learn more about the heliosphere, the protective bubble created by the sun's solar wind, and the interstellar medium beyond it. This information is crucial for understanding how our solar system interacts with the surrounding galaxy and provides a glimpse into the conditions of interstellar space, a region that has remained largely unexplored until now. Number 8. The Hubble Deep Field and the Evolution of Galaxies. The Hubble Deep Field represents one of the most profound observational campaigns in the history of astronomy. Conducted by the Hubble Space Telescope in 1995, this initiative aimed to peer into the farthest reaches of the universe, revealing a patch of sky in the constellation Ursa Major that was seemingly empty and devoid of stars or galaxies. Over 10 consecutive days, Hubble captured light from this tiny region, about 1/24 millionth of the sky, creating an image that forever changed our understanding of the universe. The Hubble Deep Field revealed a staggering number of galaxies, nearly 3,000, in a minuscule portion of the sky. These galaxies varied greatly in shape, size, and color, indicating a broad spectrum of ages and evolutionary stages. Some of the galaxies were relatively close to Earth, while others were billions of light-years away, meaning Hubble was capturing images of these galaxies as they appeared when the universe was just a fraction of its current age. This unprecedented glimpse into the early universe offered astronomers crucial insights into the evolution of galaxies. The Hubble Deep Field provided a timeline that spanned billions of years, showing how galaxies have changed over cosmic time. Some of the most distant galaxies in the Hubble Deep Field were small and irregular, suggesting that they were in the early stages of formation. This observation supports the theory that galaxies began as small structures that merged and grew into the massive galaxies we see today, like the Milky Way. Moreover, the diversity of galaxies observed in the Hubble Deep Field, from spirals to ellipticals to peculiar shapes, helped scientists piece together the processes that drive galaxy evolution. For instance, the presence of blue, star-forming galaxies alongside older, redder galaxies indicated that star formation was more rampant in the early universe and has since slowed down. The Hubble Deep Field also highlighted the importance of dark matter in galaxy formation. The distribution and interaction of galaxies in the field suggested that dark matter played a crucial role in their evolution, influencing their shapes and the rate at which they merged with others. Overall, the Hubble Deep Field provided a window into the universe's distant past, offering a profound understanding of how galaxies evolve over time. It set the stage for future deep-field observations and remains a cornerstone in our quest to understand the origins and fate of galaxies in the cosmos. Number 9. The exploration of the Kuiper Belt and the discovery of Pluto's geology. The Kuiper Belt, a distant and icy region of the solar system, represents one of the last frontiers of planetary exploration. Located beyond Neptune's orbit, this vast donut-shaped disk is home to countless icy bodies, dwarf planets, and remnants from the early solar system. First proposed by astronomer Gerard Kuiper in 1951, the Kuiper Belt was hypothesized as a region containing small, icy bodies left over from the solar system's formation. It wasn't until the early 1990s that the first Kuiper Belt object was discovered, confirming the existence of this distant region. The Kuiper Belt extends from about 30 to 55 astronomical units from the Sun with its objects composed primarily of frozen volatiles such as water, ammonia, and methane. The discovery of the Kuiper Belt provided critical insights into the origins of short-period comets and the early solar system's formation processes. As a reservoir of ancient material, the Kuiper Belt holds the potential to reveal secrets about the solar system's birth and the processes that led to the formation of planets. The most significant milestone in the exploration of the Kuiper Belt came with NASA's New Horizons mission. Launched in 2006, New Horizons was the first spacecraft designed to explore this distant region, with its primary target being Pluto, the most famous of the Kuiper Belt's inhabitants. After a journey of nearly a decade, New Horizons made its historic flyby of Pluto in July 2015, providing humanity with its first close-up images and data from this enigmatic dwarf planet. The flyby revealed Pluto as a complex and geologically active world, shattering previous assumptions that it was a frozen, inert body. New Horizons sent back images of towering mountains of water ice, vast plains of nitrogen ice, and signs of cryovolcanism. The mission's success highlighted the importance of exploring the Kuiper Belt, showing that even at the solar system's fringes, planetary bodies could be dynamic and diverse. Following its successful flyby of Pluto, New Horizons continued its journey deeper into the Kuiper Belt. On January 1, 2019, it made a close approach to another Kuiper Belt object, Arrokoth, previously known as 2014 MU-69. This small, bilobed object provided scientists with a glimpse into the early solar system's building blocks. Arrokoth's shape and surface features suggested that it formed through the gentle merging of two smaller bodies, providing valuable insights into how planets and other solar system bodies might have formed. The exploration of Arrokoth and other Kuiper Belt objects has deepened our understanding of the Kuiper Belt as a repository of primordial material. These objects have remained largely unchanged since the solar system's formation, preserving the conditions of the early solar nebula. By studying them, scientists can gain a clearer picture of the processes that led to the formation of planets and the evolution of the solar system. On the other hand, note that the exploration of the Kuiper Belt is still in its early stages, with much left to discover. Future missions could target other Kuiper Belt objects, including larger and more distant objects, to further unravel the mysteries of this remote region. The Kuiper Belt also presents a valuable opportunity to study the formation of planetary systems in other star systems, as it shares similarities with the debris disks observed around young stars. Moreover, the continued exploration of the Kuiper Belt has implications for our understanding of the solar system's boundaries. The region marks the transition from the solar system's planetary zone to the more distant and diffuse Oort cloud, the source of long-period comets. Understanding the Kuiper Belt's structure and population is key to comprehending the solar system's architecture and its interaction with the interstellar environment. Number 10. The first images of black holes and the Event Horizon Telescope. Black holes has long fascinated scientists and the public alike, largely because of the enigmatic nature of their cosmic giants. They are regions of space-time where gravity is so intense that nothing, not even light, can escape. This makes them invisible against the backdrop of space, but their presence can be inferred from their effects on nearby matter and radiation. A groundbreaking tool in the study of black holes has been the Event Horizon Telescope, also known as EHT, an international collaboration that aims to capture images of these elusive objects. It could be said that the EHT represents a monumental leap forward in observational astronomy. The project began in earnest in 2012, bringing together over 200 researchers from institutions worldwide with the goal of imaging the event horizon of a black hole. The EHT is not a single telescope, but a network of radio telescopes located at different points around the globe. By synchronizing these telescopes through a technique called very long baseline interferometry, the EHT effectively creates a planet-sized observatory with unprecedented resolution. The EHT's first major achievement was the release of the image of the supermassive black hole in the galaxy M87 in April 2019. This was a historic moment in astrophysics, as it provided the first direct visual evidence of a black hole's existence. The image showed a bright ring-like structure with a dark central region representing the shadow of the black hole against the glowing gas and plasma surrounding it. This groundbreaking result confirmed many predictions of general relativity and provided new insights into the structure and behavior of black holes. The success of the EHT then has paved the way for further explorations into the nature of black holes. Future improvements in the array, including the addition of more telescopes and the use of higher frequency observations, are expected to enhance the resolution and detail of the images. Upcoming observations will focus not only on refining the image of M87's black hole, but also on imaging the event horizon of the black hole at the center of our own Milky Way galaxy, known as Sagittarius A. Additionally, the EHT's findings are likely to have broader implications for our understanding of fundamental physics. For example, studying the behavior of matter and radiation near the event horizon may provide insights into the nature of space-time, the formation of black holes, and the processes governing their growth and interactions with their surroundings. In summary, the study of black holes and the contributions of the Event Horizon Telescope represent a profound leap in our understanding of the universe. By capturing images of these cosmic behemoths, the EHT has provided a direct glimpse into regions that were previously beyond the reach of observational astronomy, opening up new avenues for research and deepening our understanding of the most extreme objects in the cosmos. Number 11. The James Webb Space Telescope and the Early Universe. The James Webb Space Telescope has opened a new era of cosmology. Launched on December 25, 2021, Webb's advanced capabilities have significantly transformed our comprehension of the early universe, providing unprecedented insights into the cosmos's infancy. At its core, Webb's ability to peer deep into the universe is facilitated by its large, segmented mirror and its position in orbit around the second Lagrange point, about 1.5 million kilometers from Earth. This strategic location, combined with its infrared-optimized instrumentation, allows the telescope to observe the faintest and most distant objects in the universe, those that were previously beyond the reach of earlier telescopes like Hubble. One of the most groundbreaking contributions of James Webb is its capability to observe the universe's first galaxies. By looking back in time through the infrared spectrum, the telescope can detect the light from the earliest galaxies that formed shortly after the Big Bang, about 13.8 billion years ago. These observations have provided new insights into the formation and evolution of the first galaxies, revealing that galaxy formation occurred much earlier than previously thought. For instance, James Webb has identified galaxies formed only a few hundred million years after the Big Bang, challenging previous models of galaxy evolution and pushing the boundaries of our knowledge about how these structures emerged. Webb's deep-field observations have also shed light on the process of reionization, a pivotal era in the universe's history when the first stars and galaxies ionized the intergalactic medium. This period marked the transition from the cosmic dark ages to a universe filled with light. By examining the distribution and characteristics of early galaxies, James Webb has provided crucial data on the timing and nature of reionization, offering a more detailed picture of how the first cosmic structures interacted with their surroundings and contributed to the reionization of the universe. Moreover, the observatory has made significant strides in understanding the formation of stars and planetary systems. Its high-resolution infrared imaging allows scientists to observe star-forming regions obscured by cosmic dust, revealing previously hidden details about the birth of stars and the formation of protoplanetary disks. These observations are crucial for understanding the processes that lead to the formation of planetary systems, including our own. By studying these early star-forming regions, James Webb helps bridge the gap between the initial formation of stars and the eventual development of planetary systems, offering insights into the conditions that might lead to habitable planets. Another critical aspect of James Webb's mission is its ability to study the physical and chemical properties of the early universe. Through its advanced spectroscopic capabilities, the Webb telescope can analyze the light from distant galaxies and stellar objects to determine their composition, temperature, and other fundamental properties. This information is vital for understanding the chemical evolution of the universe, including the formation of heavy elements and the enrichment of the interstellar medium. By examining the spectral signatures of early galaxies and stars, James Webb provides a detailed account of how these objects contributed to the chemical makeup of the universe. In addition to its observational capabilities, findings made by James Webb have prompted a re-evaluation of theoretical models of cosmic evolution. Its data has led to new hypotheses about the formation and growth of galaxies, the nature of dark matter, and the conditions that led to the development of complex structures in the universe. These insights are reshaping our understanding of cosmological processes and prompting revisions to existing models of the early universe. The impact of James Webb extends beyond the immediate realm of galaxy and star formation. Its observations have provided a broader context for understanding the fundamental processes that shaped the universe's structure. By offering a clearer picture of the early universe, the Supreme Observatory helps scientists address some of the most profound questions in cosmology, including the nature of dark energy, the formation of the first black holes, and the origins of cosmic inflation. In summary, thanks to its advanced observational capabilities and infrared technology, the Premier Telescope has dramatically enhanced our knowledge of the cosmos's infancy. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. The neighborhood to the edge of time, the James Webb Space Telescope challenged our understanding of the cosmos and showed the universe in a way no other telescope in the past could. And in a recent remarkable observation, the $10 billion Infrared Space Observatory has focused on Mercury, which should already be a dead planet. Scientists thought the humble hunk of rock that's only slightly girthier than Earth's moon would have been battered to barrenness by the sun's intense solar radiation. It's a hostile world. The day and night sides of the planet see a temperature difference nearly 600 degrees Celsius. But Mercury has proved to be a world of contradictions, a dynamic planet that hides more surprises than scientists initially gave it credit for. And now, by using powerful telescopes like James Webb, scientists have once again lifted the veil on the secrets of the planet, revealing Mercury is not what we think. Join us as we shed light on the most enduring mysteries of the innermost planet in our solar system. Mercury is the closest planet to the Sun, orbiting at an average distance of about 57.9 million kilometers. With a diameter of just 4,880 kilometers, it is the smallest planet in the solar system, slightly larger than Earth's moon. Despite its proximity to the Sun, Mercury's surface temperatures vary dramatically, ranging from scorching highs of 430 degrees during the day to freezing lows of 180 degrees at night. Mercury's orbit is highly eccentric, meaning it is not a perfect circle, but rather an elongated ellipse. This eccentricity, combined with its rapid orbital period of just 88 Earth days, leads to fascinating orbital dynamics that have intrigued astronomers for centuries. One of the most notable features of Mercury's orbit is its 3-2 spin-orbit resonance, where the planet rotates 3 times on its axis for every 2 orbits around the Sun. The surface of Mercury is a stark, barren landscape, characterized by numerous impact craters, vast plains, and towering cliffs. The planet's surface bears the scars of a violent history, with craters ranging in size from tiny pits to massive basins hundreds of kilometers across. The largest of these is the Coverup Basin, a massive impact crater over 1,500 kilometers in diameter, formed by a colossal collision with an asteroid or comet billions of years ago. Mercury's surface is also home to a network of long, steep cliffs known as Lobat scarps. These scarps are thought to have formed as the planet's interior cooled and contracted, causing the crust to buckle and fracture. Some of these cliffs rise as high as 3 kilometers and stretch for hundreds of kilometers across the planet's surface. Despite its barren appearance, Mercury's surface is not entirely devoid of activity. Recent observations have revealed evidence of volcanic activity in the planet's past, with smooth plains and ancient lava flows suggesting that Mercury once had a more geologically active history. However, unlike Earth or Venus, Mercury's volcanic activity appears to have ceased billions of years ago, leaving behind a frozen, lifeless landscape. One of the most puzzling aspects of Mercury is its magnetic field. Mercury is the only terrestrial planet besides Earth to have a global magnetic field, although it is much weaker than Earth's. The existence of this magnetic field was first confirmed by NASA's Mariner 10 spacecraft in the 1970s, but its origin remains a mystery. A planet's magnetic field is typically generated by the motion of molten iron within its core, a process known as the dynamo effect. However, given Mercury's small size and proximity to the Sun, scientists were surprised to find that the planet still has an active dynamo. Theories suggest that Mercury's core may contain a higher proportion of iron than previously thought, or that the planet's core has a unique composition or structure that allows it to sustain a magnetic field. Adding to the mystery is the fact that Mercury's magnetic field is not symmetrical. It is significantly stronger in the northern hemisphere than in the southern hemisphere, a phenomenon that is not yet fully understood. Some scientists believe that this asymmetry may be due to variations in the planet's core or mantle, while others suggest that it could be a result of interactions between the magnetic field and the solar wind. What's more, unlike Earth, Mercury has no significant atmosphere. Instead, the planet is surrounded by an extremely thin layer of atoms known as an exosphere. This exosphere is composed primarily of oxygen, sodium, hydrogen, helium, and potassium, and is constantly replenished by the solar wind, micrometeoroid impacts, and the release of volatile materials from the planet's surface. The existence of Mercury's exosphere was first confirmed by Mariner 10 and later studied in greater detail by NASA's Messenger spacecraft. The exosphere is so tenuous that it is barely detectable, with an atmospheric pressure less than a trillionth of Earth's. Despite its thinness, the exosphere plays a crucial role in the planet's interaction with the solar wind and the space environment. One of the most fascinating aspects of Mercury's exosphere is its dynamic nature. The atoms in the exosphere are constantly being stripped away by the solar wind, only to be replaced by new atoms from the surface. This continuous exchange of particles creates a delicate balance that can be easily disrupted by solar activity, leading to fluctuations in the composition and density of the exosphere. Mercury's most striking feature is its unusually large core, which makes up about 85% of the planet's radius. This core is believed to be composed primarily of iron, with smaller amounts of nickel and other elements. The sheer size of Mercury's core relative to its overall size is unique among the terrestrial planets and has led to much speculation about the planet's formation and history. One of the leading theories suggests that Mercury may have once been a much larger planet, with a thick rocky mantle similar to Earth's. However, a giant impact early in the planet's history could have stripped away much of this mantle, leaving behind the dense metallic core we see today. This giant impact hypothesis is supported by the planet's high density and the relative scarcity of silicate materials on its surface. The core of Mercury is also thought to be partially molten, which may explain the planet's magnetic field. But the exact state of the core, whether it is completely liquid, partially solid, or something in between, remains an open question. Understanding the nature of Mercury's core could provide valuable insights into the formation and evolution of the inner planets in our solar system. However, given its proximity to the Sun and the extreme conditions on its surface, Mercury is a challenging planet to study. Mercury has been visited by only 2 spacecraft, NASA's Mariner 10 and Messenger missions. These missions have provided the bulk of our current knowledge about the planet, but what is really interesting about Mercury are the things that can't be seen. And now, thanks to incredible research efforts, scientists have finally given us some remarkable clues that could upend our understanding of this enigmatic world. In a groundbreaking revelation, scientists have discovered that Mercury, the innermost planet in our solar system, may harbor salt glaciers that could support life beneath its sun-scorched surface. This discovery is not only a significant leap in our understanding of the planet's geology, but also raises intriguing possibilities about the potential for life in environments once deemed inhospitable. The key to this new discovery lies in the data gathered by NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015. Messenger's suite of scientific instruments provided unprecedented insights into the planet's surface composition, magnetic field, and geological history. One of the most surprising findings from Messenger's mission was the detection of unusual surface features that suggested the presence of volatile substances, including water ice and salts. Researchers have long known that Mercury's poles contain deposits of water ice, trapped in permanently shadowed craters. These craters, located in the planet's polar regions, are shielded from the sun's harsh rays, allowing ice to accumulate and persist. However, the discovery of salt glaciers has added a new dimension to our understanding of Mercury's polar deposits. Analysis of Messenger's data revealed features that resemble glaciers on Earth, but with a twist. These so-called salt glaciers are formed from a mix of salts, such as sodium chloride and magnesium sulfate, and ice. The presence of these salt deposits suggests that, at some point in Mercury's history, liquid water may have been present on the planet's surface and subsequently evaporated, leaving behind these saline features. The formation of salt glaciers on Mercury involves several stages. First, volatile compounds such as water and various salts were likely present in the planet's crust. Over time, geological processes, including impacts and volcanic activity, would have brought these materials to the surface. When Mercury's surface temperatures fluctuated, especially in the shadowed regions near the poles, water ice could have formed and mixed with salts. The persistence of these salt glaciers is indicative of a complex climatic history. The planet's axial tilt is minimal, meaning that its poles receive very little direct sunlight. This, combined with the extremely low temperatures in the shadowed craters, has allowed these glaciers to remain relatively stable over geological timescales. The discovery of salt glaciers on Mercury prompts a re-evaluation of the planet's potential to support life. While the current conditions on Mercury are inhospitable to life as we know it, the presence of salts and ice raises the possibility that microbial life could exist in subsurface environments, similar to how life is hypothesized to survive beneath the icy crusts of moons like Europa and Enceladus. In addition to the presence of water ice and salts, the idea that Mercury once had a more temperate climate further fuels speculation about its potential for life. If liquid water was once stable on the surface, it opens up the possibility that life could have had a chance to develop during that period. Even if no evidence of life is found, these findings can provide valuable insights into the planet's geological history and the processes that shaped its surface. Another remarkable discovery: recent scientific research has unveiled a breathtaking possibility. Mercury might be hiding a treasure trove unlike anything we could have imagined, a diamond layer 15 kilometers thick. To understand how Mercury could host such an incredible deposit of diamonds, we first need to appreciate the planet's unique geological and environmental conditions. As told, Mercury is a planet of extremes. With temperatures fluctuating from a blistering 400 degrees during the day to a bone-chilling 180 degrees at night, the surface is subject to tremendous thermal stress. This temperature variation alone suggests that the planet's surface could be a breeding ground for complex chemical reactions. Additionally, Mercury's lack of a substantial atmosphere, unlike Earth's thick blanket of air, leaves it exposed to the harsh solar wind, a constant stream of charged particles from the sun. These factors combine to create an environment where only the toughest materials can endure. This leads us to the key ingredient in our story: carbon. We all know that carbon is an essential element in the formation of diamonds. Under the right conditions, extreme pressure and temperature, carbon atoms can rearrange themselves into a crystal structure, creating diamonds. On Earth, diamonds are formed deep within the mantle, where pressures are immense. They are then brought to the surface through volcanic eruptions encapsulated in kimberlite pipes. But Mercury's formation and evolution took a different path. Recent studies suggest that Mercury's formation was marked by a cataclysmic event. During the early days of the solar system, a massive impact stripped away much of Mercury's outer layers, leaving it with an unusually large core relative to its size. This event could have also compressed large amounts of carbon deep within the planet, creating conditions ripe for diamond formation. Unlike Earth, where tectonic activity and erosion constantly reshape the surface, Mercury's geological activity is limited. This means that any diamonds formed in its early history could have remained largely undisturbed, accumulating over billions of years to form a thick layer. The idea of a 15-kilometer thick diamond layer on Mercury might sound like science fiction, but it's grounded in solid scientific principles. If Mercury's early history did involve massive impacts and intense pressure, it's plausible that much of the planet's carbon was converted into diamonds. Over time, as Mercury cooled and solidified, these diamonds could have settled into a stable layer beneath the surface. Moreover, Mercury's proximity to the Sun means it has been bombarded with meteoroids for billions of years. These impacts could have further driven carbon deep into the planet's crust, adding to the growing diamond reservoir. Some scientists hypothesize that the upper crust of Mercury could be a mix of regolith and diamond-rich rock, with the diamonds concentrated at deeper levels where pressures were once highest. One might wonder how such an extraordinary claim could be substantiated. The challenge lies in the fact that Mercury is not an easy planet to study. Its proximity to the Sun makes it difficult for telescopes to observe, and sending spacecraft to Mercury presents its own set of challenges. However, the Messenger spacecraft, which orbited Mercury from 2011 to 2015, provided a wealth of data that has since been analyzed to offer clues. Messenger's X-ray and gamma-ray spectrometers detected higher than expected levels of carbon on Mercury's surface, particularly in certain regions. This carbon, found in the form of graphite, could be the remnant of a once more extensive carbon layer that has since been weathered down by meteoroid impacts and solar wind. If graphite exists in significant quantities, it strengthens the case for diamonds lying beneath, as graphite and diamond are different forms of carbon. Moreover, the high radar reflectivity observed in some of Mercury's craters is another piece of evidence. Radar signals bounce back strongly from highly reflective surfaces, such as ice or metal. However, diamonds are also excellent reflectors of radar waves, meaning that these bright spots on Mercury's radar map could be hinting at diamond-rich areas. Regardless, to fully understand the implications of these discoveries, future missions to Mercury are crucial. The next major mission to Mercury is Bepi Colombo, a joint mission between the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA. Launched in October 2018, Bepi Colombo is currently en route to Mercury, with its arrival scheduled for December 2025. This mission is named after Giuseppe Bepi Colombo, an Italian scientist who first explained the relationship between Mercury's rotation and its orbit around the Sun. Bepi Colombo consists of two spacecraft, the Mercury Planetary Orbiter, or MPO, developed by ESA, and the Mercury Magnetospheric Orbiter, or MMO, developed by JAXA. The two spacecraft will work in tandem to study Mercury's surface, interior, exosphere, and magnetosphere in unprecedented detail. The MPO will focus on the planet's surface and interior, mapping its topography, composition, and geological features, while the MMO will study the planet's magnetosphere and its interaction with the solar wind. One of the key objectives of Bepi Colombo is to build on the discoveries made by Messenger and answer some of the lingering questions about Mercury. For example, Bepi Colombo will investigate the origin of Mercury's magnetic field, which is much weaker than Earth's, and is likely generated by a partially molten core. The mission will also study the composition of the planet's surface, including the mysterious hollows, bright, shallow depressions that appear to be unique to Mercury. In addition to its scientific goals, Bepi Colombo will test advanced technologies that could be used in future missions to Mercury and other planets. For example, the mission's solar electric propulsion system, which uses ionized xenon gas to generate thrust, could pave the way for more efficient space travel in the future. While Bepi Colombo represents the next significant step in Mercury exploration, scientists are already looking ahead to future missions that could build on its findings. These missions could take various forms, from orbiters and landers to sample return missions, and even human exploration. One of the most exciting prospects for future Mercury exploration is the idea of sending a lander to the planet's surface. A lander would provide an unprecedented opportunity to study Mercury's geology up close, analyze its surface composition, and conduct experiments that are not possible from orbit. For example, a lander could drill into the surface to study the planet's interior structure or deploy instruments to measure the heat flow from the interior to the surface, which could provide clues about the planet's thermal evolution. However, designing a lander capable of surviving Mercury's extreme conditions presents significant challenges. The lander would need to be equipped with a sophisticated thermal control system to protect it from the intense heat of the sun, as well as radiation-hardened electronics to withstand the harsh environment. Additionally, landing on Mercury's surface is no easy feat, given the planet's low gravity and lack of atmosphere, which makes it difficult to slow down the descent. Despite these challenges, there have been several proposals for Mercury lander missions. One such proposal is the Mercury Surface Element, also known as MSE, a concept developed by ESA as part of the Bepi Colombo mission. Although the MSE was ultimately not included in the mission, the concept could serve as the basis for future lander missions. Another proposal is the Mercury Lander Mission concept, developed by NASA's Jet Propulsion Laboratory, or JPL, which envisions a lander equipped with a suite of scientific instruments to study the planet's surface and interior. Another ambitious goal for future Mercury exploration is the return of samples from the planet's surface to Earth. A sample return mission would allow scientists to conduct detailed analyses of Mercury's surface material in laboratories on Earth, providing insights that are not possible with remote sensing or in situ measurements. For example, scientists could study the isotopic composition of Mercury's rocks to learn more about the planet's formation and evolution, or search for traces of volatile elements that could shed light on the history of water on the planet. Designing a sample return mission to Mercury poses several technical challenges. The spacecraft would need to carry a lander capable of collecting samples, as well as a return vehicle to bring the samples back to Earth. The mission would also need to overcome the challenges of operating in Mercury's extreme environment, as well as the difficulties of launching a spacecraft from the planet's surface. Despite these challenges, advances in technology and lessons learned from previous sample return missions, such as NASA's OSIRIS-REx mission to the asteroid Bennu, could make a Mercury sample return mission feasible in the future. While human exploration of Mercury is still a distant prospect, it is not entirely out of the realm of possibility. Advances in space technology, such as nuclear thermal propulsion and advanced life support systems, could one day make it possible for humans to visit Mercury and conduct scientific research on the planet's surface. Human missions to Mercury would likely be similar in scope to the Apollo missions to the Moon, with astronauts landing on the surface for short durations and conducting experiments before returning to Earth. Human exploration of Mercury would offer several unique opportunities for scientific research. For example, astronauts could conduct geological surveys of the planet's surface, study its magnetic field and interaction with the solar wind, and search for signs of past or present water. Additionally, human missions to Mercury could serve as a stepping stone for future exploration of other planets in the inner solar system, such as Venus or Mars. The future missions to Mercury have the potential to revolutionize our understanding of the planet and its place in the solar system. By studying Mercury's surface, interior, atmosphere, and magnetosphere in greater detail, scientists hope to answer key questions about the planet's formation and evolution, its geological history, and its interaction with the Sun. One of the key scientific objectives of future Mercury missions is to understand the planet's unique composition. Mercury has a much higher metal content than any other planet in the solar system, with a large iron core that makes up about 85% of its radius. This unusual composition has led scientists to propose several theories about Mercury's formation, including the possibility that the planet was once much larger and lost much of its outer layers in a giant impact. Future missions could provide the data needed to test these theories and determine the true origin of Mercury's composition. Another important objective is to study Mercury's magnetic field and its interaction with the solar wind. Unlike Earth, Mercury's magnetic field is weak and highly variable, with frequent reconnection events that create intense bursts of radiation near the planet's surface. By studying these phenomena in greater detail, scientists hope to gain insights into the dynamics of planetary magnetic fields and their role in protecting planets from solar radiation. Future missions could also shed light on the history of water on Mercury. Although the planet is thought to be too hot for liquid water to exist on its surface, MESSENGER discovered evidence of water ice in permanently shadowed craters at the poles. Bepi Colombo and future missions could study these ice deposits in greater detail, potentially revealing clues about the sources of water in the inner solar system and the history of volatiles on Mercury. Finally, future missions to Mercury could help answer fundamental questions about the formation and evolution of the solar system, and by extension, offer clues about the conditions that led to the formation of Earth and other terrestrial planets. One of the most intriguing aspects of Mercury is its unusually high metal content. The planet has an iron-rich core that accounts for about 85% of its radius, which is proportionally much larger than Earth's core. This composition suggests that Mercury experienced a different formation and evolutionary history compared to the other terrestrial planets. Understanding why Mercury is so metal-rich could shed light on the processes that influenced planetary formation in the early solar system. There are several hypotheses about Mercury's high metal content. One theory suggests that Mercury might have formed from material that was metal-rich from the beginning, possibly as a result of the Sun's early influence. Another hypothesis proposes that Mercury originally had a silicate-rich mantle similar to Earth's, but a massive impact during its formation stripped away much of this mantle, leaving behind a metal-rich core. Studying Mercury in detail could help scientists determine which of these scenarios is more accurate, providing insights into the conditions that existed in the inner solar system during its formation. Mercury is the only other terrestrial planet besides Earth that has a significant magnetic field, although it is much weaker than Earth's. The presence of this magnetic field suggests that Mercury has a partially molten outer core, which generates the field through the dynamo effect. By studying Mercury's magnetic field, scientists can learn more about the planet's core dynamics and how its magnetic field has evolved over time. Understanding Mercury's magnetic field could also provide clues about the early magnetic history of Earth. Earth's magnetic field is crucial for protecting our planet from solar and cosmic radiation, making it a key factor in the development and sustenance of life. By comparing Earth's magnetic field with Mercury's, scientists can gain a better understanding of the factors that influence magnetic field generation in terrestrial planets and how these fields evolve. This knowledge could also help scientists predict the future behavior of Earth's magnetic field, which is currently weakening. Mercury's surface is heavily cratered, similar to the Moon, but it also has unique features such as large cliffs or lobate scarps that run for hundreds of kilometers. These scarps are thought to have formed as Mercury's core cooled and contracted, causing the planet's surface to shrink and buckle. The presence of these scarps suggests that Mercury's geological history is still active, albeit at a much slower rate than on Earth. Studying Mercury's surface features can provide insights into the planet's geological history and the processes that have shaped its surface over billions of years. For instance, understanding the formation of lobate scarps can help scientists learn more about the thermal evolution of Mercury's core and mantle. This, in turn, can offer clues about the thermal histories of other terrestrial planets, including Earth. Mercury also has regions known as smooth plains, which are believed to be the result of ancient volcanic activity. The presence of these plains suggests that Mercury had a more geologically active past than previously thought. By studying the volcanic history of Mercury, scientists can learn more about the planet's internal heat generation and how it has changed over time. This information could be valuable for understanding the volcanic history of Earth and other terrestrial planets, as well as the role of volcanism in planetary evolution. Mercury has a tenuous atmosphere, or exosphere, composed mainly of hydrogen, helium, oxygen, sodium, and potassium. Unlike Earth's thick atmosphere, Mercury's exosphere is constantly being replenished by particles from the solar wind, surface interactions, and outgassing from the planet's interior. Studying Mercury's exosphere can provide valuable information about the interactions between the solar wind and planetary surfaces. The study of Mercury's exosphere is particularly important because it offers a unique opportunity to observe how a planet's surface and atmosphere interact with the solar wind. Since Mercury is so close to the Sun, it experiences much stronger solar wind conditions than Earth. By understanding how Mercury's exosphere responds to these conditions, scientists can gain insights into the processes that shape planetary atmospheres in general. This knowledge can also be applied to Earth, helping scientists better understand how our planet's atmosphere interacts with the solar wind, and how this interaction has influenced Earth's evolution. Mercury's unique characteristics challenge many existing models of planetary formation. Traditional models suggest that terrestrial planets formed from the gradual accumulation of planetesimals in the protoplanetary disk. However, Mercury's high metal content, weak magnetic field, and unusual surface features suggest that its formation involved processes that are not fully explained by these models. Studying Mercury in greater detail can help scientists refine these models and develop new theories about planetary formation. For example, understanding why Mercury has such a large iron core relative to its size could provide insights into the role of giant impacts in planetary formation. Similarly, studying Mercury's magnetic field and geological history can help scientists develop more accurate models of how terrestrial planets evolve over time. Mercury offers a unique opportunity for comparative planetology, the study of planets by comparing their properties and histories. By comparing Mercury with Earth, scientists can identify similarities and differences that provide insights into the process that shaped both planets. For instance, both Mercury and Earth have metallic cores and magnetic fields, but the differences in their sizes, compositions, and geological histories can help scientists understand the factors that influence planetary evolution. One key area of comparative planetology is understanding the role of size in planetary evolution. Mercury is much smaller than Earth, which has significant implications for its thermal evolution, magnetic field generation, and geological activity. By studying these differences, scientists can learn more about how a planet's size influences its evolution and what this might mean for Earth. Another area of interest is the study of planetary atmospheres. While Earth has a thick atmosphere that supports life, Mercury's exosphere is extremely thin and constantly influenced by the solar wind. Comparing these two atmospheres can provide insights into the factors that determine atmospheric retention and composition, which are crucial for understanding the conditions necessary for life. Mercury's proximity to the Sun and its unique characteristics make it a valuable target for studying the early solar system's evolution. The planet's high metal content, weak magnetic field, and unusual surface features suggest that it has experienced processes that are not fully understood and that may have been more common in the early solar system. By studying Mercury, scientists can gain insights into the processes that influence the formation and evolution of the solar system as a whole. For example, understanding Mercury's formation and evolution could provide clues about the distribution of materials in the protoplanetary disk, the role of giant impacts in planetary formation, and the thermal histories of terrestrial planets. These insights could also help scientists better understand the conditions that led to the formation of Earth and other habitable planets. In short, while Mercury is a small planet with a big story to tell, its unique characteristics make it a key target for understanding the formation and evolution of the solar system, including Earth. By studying Mercury's composition, magnetic field, geological history, and exosphere, scientists can gain valuable insights into the processes that shaped our planetary neighborhood. These insights can help refine existing models of planetary formation and evolution, providing a clearer picture of how Earth and other terrestrial planets came to be. As we continue to explore Mercury, we are likely to uncover even more secrets about the early solar system and the forces that shape the world we live on today. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. For nearly 5 decades, NASA's Voyager 1 spacecraft has been journeying through the vast expanse of space, becoming the farthest human-made object from Earth. Originally launched on September 5, 1977, the spacecraft's primary mission was to explore the outer planets of the solar system: Jupiter, Saturn, Uranus, and Neptune. Having accomplished that, Voyager 1 has continued its mission, sending back invaluable data from beyond the heliosphere, the protective bubble of charged particles surrounding our solar system. But now, after 47 years in the depths of interstellar space, Voyager 1 has made a new discovery that is raising both awe and concern. Even Bill Nye, known as the Science Guy and a renowned science educator and advocate, has publicly commented on Voyager 1's latest finding, calling it terrifying. This statement has stirred curiosity and alarm across the scientific community and beyond. But what exactly has Voyager 1 discovered that is so unsettling? To understand the gravity of this revelation, we must delve into the mission's history, its journey through the solar system, and the implications of its recent discovery. Before we discuss Voyager 1's startling discovery, it's essential to appreciate the magnitude of its journey. Launched at the height of the space age, Voyager 1's mission was initially designed to last just 4 years. However, thanks to the durability of its systems and the foresight of its creators, it has survived for nearly 5 decades, providing scientists with a treasure trove of data about the outer reaches of our solar system and beyond. Voyager 1's primary accomplishments in the early years of its mission were its close encounters with Jupiter and Saturn. And far exceeding all the expectations, the spacecraft sent back stunning images and data that forever changed our understanding of the outer planets. Voyager 1 captured unprecedented views of Jupiter's Great Red Spot and detailed images of Saturn's intricate ring system. Perhaps one of the most significant discoveries was the detection of active volcanism on Jupiter's moon Io, marking the first time active volcanoes had been observed on another celestial body. This revelation reshaped planetary science and sparked new questions about the geological activity on other moons in our solar system. Voyager 1 also provided humanity's first close-up look at Titan, Saturn's largest moon, which scientists had long suspected might harbor complex atmospheric chemistry. The mission revealed that Titan's thick atmosphere was rich in nitrogen and organic molecules, foreshadowing future missions that would investigate the possibility of life or prebiotic chemistry on this intriguing moon. After completing its primary objectives, Voyager 1 embarked on its extended mission to explore the outermost regions of the solar system. As the spacecraft ventured farther from the Sun, it continued to break records, becoming the farthest human-made object in existence. But the most groundbreaking phase of its mission came in 2012, when Voyager 1 became the first spacecraft to enter interstellar space, a region beyond the influence of our Sun's magnetic field. Crossing into interstellar space was a monumental achievement for humanity, marking the first time a spacecraft had left the heliosphere, the bubble-like region dominated by solar wind and magnetic fields. This milestone opened a new frontier for scientific exploration, enabling Voyager 1 to study the environment between stars, offering insights into a part of space that had never before been directly observed. To appreciate the significance of Voyager 1's discovery, it's important to understand what interstellar space is. Interstellar space refers to the region beyond the heliosphere, the bubble-like region of space dominated by the Sun's solar wind and magnetic field. This area is characterized by the presence of particles from other stars, cosmic rays, and the interstellar medium, which is composed of gas and dust. The boundary between the heliosphere and interstellar space is called the heliopause. Beyond this point, the influence of the Sun's magnetic field and solar wind diminishes, and Voyager 1 has been sending back data from this new frontier since 2012. What it has discovered in the years since has been both fascinating and, as Bill Nye has noted, potentially unsettling. According to Bill Nye and other experts, Voyager 1's most recent discovery suggests that interstellar space may be far more hostile and unpredictable than previously thought. The spacecraft has detected unusually high levels of cosmic rays and other forms of radiation, along with unexpected fluctuations in the density of the interstellar medium. One of the most significant findings is the detection of plasma waves, which are essentially ripples in the charged particles of space. Voyager 1 had previously detected such waves, but recent data indicate that these waves are far more intense than expected. The spacecraft's instruments recorded shock waves, which may be the result of massive stellar explosions, supernovae sending powerful shock waves through the galaxy. These shock waves, traveling across vast distances, appear to have collided with the boundary of the heliosphere, potentially weakening it and allowing more dangerous cosmic radiation to penetrate the bubble that surrounds our solar system. The idea that the heliosphere could be breached or weakened is alarming, because it suggests that Earth and the rest of the planets could be exposed to higher levels of cosmic radiation than previously predicted. Bill Nye's use of the word terrifying is not hyperbole. The heliosphere plays a crucial role in shielding the solar system from the harsh environment of interstellar space. Without this protective barrier, planets, including Earth, would be more vulnerable to the harmful effects of cosmic rays and high-energy particles, which can have devastating impacts on both technology and biological life. For one, cosmic rays can pose a serious threat to astronauts and future space explorers. Increased exposure to radiation can lead to a higher risk of cancer and other health issues. This could have a major impact on future space missions, especially those planning to explore Mars or beyond. Spacecraft and space stations would need additional radiation shielding, which would add to the complexity and cost of such missions. On Earth, an increase in cosmic radiation could interfere with satellite communications, GPS systems, and other technology that relies on sensitive electronic components. Solar storms, which are already known to disrupt communications and power grids, could become more frequent and intense as the heliosphere weakens. In essence, Voyager 1's discovery may have far-reaching implications not just for space exploration, but for life on Earth as well. What's more, the discovery of powerful plasma waves and the weakening of the heliosphere forces scientists to rethink some long-held assumptions about the solar system's place in the galaxy. For decades, the heliosphere was considered a relatively stable shield, protecting us from the harsh environment of interstellar space. However, Voyager 1's data suggest that this shield may be more fragile than we thought. In light of this discovery, some scientists are now questioning whether the solar system is entering a more dangerous region of the galaxy. The heliosphere, it seems, is not impenetrable, and as the Sun continues to age, its ability to maintain this protective bubble could weaken further. Bill Nye's comments reflect the growing concern within the scientific community about the long-term consequences of Voyager 1's findings. If the heliosphere is indeed being weakened by external forces, such as supernova shockwaves, it could mean that the solar system is more exposed to the dangers of interstellar space than previously imagined. Another significant discovery made by Voyager 1 in interstellar space is related to the magnetic field. Scientists have long been interested in understanding the strength and orientation of the magnetic field in the interstellar medium, as it plays a crucial role in shaping the behavior of cosmic rays and the structure of the galaxy. When Voyager 1 crossed into interstellar space, it found that the magnetic field in the region just outside the heliosphere was surprisingly aligned with the Sun's magnetic field. This was unexpected, as many models predicted that the interstellar magnetic field would be oriented differently from the solar magnetic field. This discovery has led scientists to reconsider how the Sun's magnetic field interacts with the interstellar medium and has sparked new questions about the nature of the boundaries between star systems. Moreover, Voyager 1's exploration of interstellar space is not just important for understanding our solar system, it also provides a window into the broader structure of the galaxy. By studying the interactions between the heliosphere and the interstellar medium, scientists can gain insights into how other star systems behave as they move through the galaxy. The data from Voyager 1 is helping to refine models of how stars and their magnetic fields interact with the space around them, contributing to a more complete picture of the Milky Way. Additionally, Voyager 1's findings have implications for the search for life beyond Earth. The spacecraft's data on cosmic rays and interstellar plasma are relevant to understanding the conditions that might exist in other star systems. For example, high levels of cosmic rays could affect the habitability of planets orbiting other stars by influencing their atmospheres and potentially impacting the development of life. By providing direct measurements of these conditions, Voyager 1 is helping to answer fundamental questions about the nature of space and the potential for life elsewhere in the universe. In short, Voyager 1's mission is a testament to the durability of human ingenuity and the thirst for exploration. Although the spacecraft is now more than 15 billion miles from Earth, it continues to operate, sending back data that is reshaping our understanding of the cosmos. Its journey through interstellar space marks a historic achievement in space exploration, and the data it collects will continue to provide insights for decades to come. Voyager 1 has far outlived its original mission, and while its power supply will eventually dwindle, its legacy will endure. The spacecraft carries with it the golden record, a time capsule of Earth's sounds, images, and greetings intended for any intelligent beings that might encounter it in the distant future. This symbolic gesture reflects the broader purpose of Voyager 1's mission: to explore the unknown, to seek answers about our place in the universe, and to share the story of humanity's quest for knowledge. As Voyager 1 continues its silent journey through the stars, it serves as a reminder of the incredible achievements of human space exploration and the endless possibilities that lie ahead. After 47 years, Voyager 1 remains a beacon of scientific discovery, illuminating the nature of space beyond our solar system and expanding the boundaries of human knowledge. In a stunning revelation, scientists have just announced that they have found the longest, strongest black hole jets of all time discovered, and it's causing us to rethink much of what we thought was certain. Named Porphyrion, this is the largest black hole jet system ever discovered. Its black hole-powered jets span a fantastic 24 million light-years in size, the largest structure created by a single object in the known universe. Black hole jets themselves aren't necessarily so rare. Most large galaxies house supermassive black holes at their centers, and most of these black holes are millions or even billions of times the mass of our own sun. Under typical conditions, galaxies are relatively quiet. They aren't merging. They aren't interacting with a neighbor. They aren't actively feeding on a source of matter. And they're only forming stars at a slow, steady rate, dependent on the amount of gas they possess in their disks and halos. These conditions describe most galaxies, including the Milky Way and Andromeda, not only at present, but during most of the history of the universe. However, galaxies go through periods of time where things are anything but typical. Galaxies do merge, as large galaxies gobble up smaller, more common ones, and also when two or more large galaxies collide and join together. Galaxies interact gravitationally, and when they experience close encounters with one another, the uneven pull on the internal matter causes star formation episodes and can pull gas, stars, and more onto the central black hole. All sorts of types of matter can funnel material into the galactic center, where the supermassive black hole will feast on it. And sometimes, stars form in great bursts, not only in the central regions of galaxies, but sometimes all throughout it. Any of these events, which are rare today but were far more common in the distant past, can activate a galaxy's central black hole. In the nearby universe, we see numerous examples of active galaxies. Messier 87, the giant elliptical galaxy at the heart of the Virgo cluster, shows large-scale features that appear across multiple wavelengths of light, including an optical jet that's more than 5,000 light-years long. Centaurus A is the closest active galaxy, located just 11 million light-years away, with emissions ranging from long-wavelength radio light to energetic X-ray light. And Hercules A, a supergiant elliptical galaxy located an impressive 2 billion light-years away, famously exhibits two vast radio lobes that its supermassive black hole is blowing well beyond the galaxy itself into the intergalactic medium. The extent of these jets can be large, larger than the stellar or gaseous extent of any known galaxy, whereas the largest galaxy known today is IC 1101 at the center of galaxy cluster Abell 2029, with an end-to-end extent of around 6 million light-years. That's peanuts compared to the largest black hole jet previously known. That honor belongs to Alcyonius, which was determined in 2022 to have its giant radio lobes span a distance of an impressive 16 million light-years from one end to the other. Found by Martin Oe, then finishing his PhD studies at Leiden University, its extent was the largest structure ever produced by a single object known at the time. Alcyonius, for a while, seemed to be as large as it gets for these radio jets. It was the first structure created by a single object known to approach the scale of the cosmic web, the large-scale structure of the universe, characterized by a web of interconnected filaments of matter, separated by vast cosmic voids, or regions virtually devoid of stars and galaxies. In the nearby universe, the typical radius of a cosmic void is somewhere around 50-70 million light-years, meaning that Alcyonius was an impressive 20-30% the size of a cosmic void. Many didn't expect that larger such jets would be possible. Observationally, none had been discovered, and from a theoretical viewpoint, there were many reasons to expect that 16 million light-years, or about 5 megaparsecs, would be the maximum size that such jets would be able to achieve, assuming we understood the physics that drove them. Typical jets only span a few galaxy diameters, largely limited by factors like the amount of matter falling into the supermassive black hole, the duration of time that the supermassive black hole remains active, and the density of the intergalactic medium, which resists the outward motion and expansion of these energetic jets. It was also thought that as we looked back earlier and earlier into the history universe, there would be a greater fraction of active galaxies, but those same size-scale limits of these jets, both from an absolute perspective and relative to the size of a standard cosmic void, would get no larger. With a brand new paper published in the journal Nature on September 18, 2024, those expectations have now been demolished. A team of scientists, led by Martin Oe, who's now a postdoctoral researcher at Caltech, has discovered a brand new structure in the universe. The first one that actually is on the scale of the cosmic web itself. The structure, which they name Porphyrion, which, like Alcyonius, takes its name after one of the gigantes from Greek mythology, is a whopping 24 million light-years from end to end, and isn't exactly nearby, but rather comes to us from an impressive 7.5 billion years ago, when the universe was only about half of its present size. It's not at all an exaggeration to state that this revolutionizes our view of how large and massive cosmic jets can get, and causes us to reevaluate their potential role in shaping the universe as we see it today. Whereas Alcyonius, which is relatively close by, is only 30% the extent of a cosmic void's radius. Porphyrion is about 66%, or 2/3, the radius of a cosmic void at that epoch in cosmic history. We're not talking about a few times the diameter of a galaxy here, like we normally do for black hole jets. Instead, Porphyrion's jets are a whopping 140 times the diameter of the Milky Way from end to end, by far the largest ever discovered. This has enormous implications for how the universe grew up. Because galaxy mergers, including major mergers, galaxy-galaxy interactions, and gas infall onto galaxies, were all more common in the younger universe, we have every reason to expect that these black hole jets, including extremely large and energetic black hole jets, were far more common in the early universe than they are today. Given that the universe was smaller back then, as the universe and the sizes of voids and filaments within it expands over time, This hints that massive black hole jets could have played an important role in shaping the largest-scale features in the universe itself. For example, the power of this jet system is enormous, estimated at around 10 to the power of 39 watts by the study authors. That's more than 2 trillion times the amount of power emitted by the Sun, and more power than gets emitted by all the stars in the galaxy that created Porphyrion put together. The extent of this jet system indicates an advanced age for it, indicating that the active black hole powering it must have been active for around 1 billion years at least, an extremely long time for a galaxy to remain active. Other than a major merger, or perhaps a series of major mergers, there's no known source of matter that can power an active galaxy for such a long duration. For these jets to grow to such an enormous extent requires a series of remarkable events to occur. First, the jets need to blast through the medium around the black hole, then through the interstellar gas and dust within the galaxy. Next, breaking through the circumgalactic medium that extends for hundreds of thousands of light years around the galaxy, until it finally penetrates into intergalactic space. The high power of these jets, especially over long lifetimes, normally leads to these jets and those giant radio lobes spreading out over time. In the case of Porphyrion, this did not occur. Porphyrion's existence demonstrates, unexpectedly, that black hole jets can persist in a coherent fashion for much longer than was previously known. The power of these jets, cumulatively over time, allows us to estimate how significantly the mass of the black hole that powers it must have grown during this time. Although black holes are notoriously messy eaters, much of the matter that falls onto them does indeed get absorbed, growing the mass of the black hole. Just from the creation of these massive jets, we can infer that the black hole at the center of Porphyrion grew by at least 1 to 1 billion solar masses during the production of this jet, was already supermassive at for 1 billion solar masses or more prior to the jet turning on, and did not have its orientation significantly perturbed during the entirety of the time it was active. There are also significant implications for the intergalactic medium that Porphyrion's discovery carries along with it. Because these systems should have been far more common early on in cosmic history, they could be heavily responsible for not only injecting energy into the intergalactic medium, but could be the primary culprit behind why the intergalactic medium is so heavily magnetized. We'd previously considered that magnetism arises on enormous cosmic scales from stars and stellar processes, but those are largely confined to galaxies. There's a physics mechanism known as a Biermann battery, where electrons and ions will separate even when subjected to purely gravitational forces, and that's been considered as a culprit for magnetizing the intergalactic medium, as well as amplified seed magnetic fields arising from processes in the very early universe. However, now there's a new contender: black hole jets, penetrating so deeply into intergalactic space and even into cosmic voids, could also magnetize the intergalactic medium. It was long thought that magnetohydrodynamic instabilities would destabilize these jets and prevent them from being so large and remaining coherent. Porphyrion has definitively shown us that is not the case at all, even early on, when the universe was around 10 times as dense as it is today. When you find the first of any new phenomena or class of object, of course, you have to wonder not only if there are others like it, but how common they are. Although Porphyrion is the largest black hole jet system ever discovered, and all other comparably large ones are much closer to us, and hence are found when the universe is much larger and more evolved, there are good reasons to expect that this is just the proverbial tip of the iceberg when it comes to incredibly long, powerful, enduring black hole jet systems. One notable aspect of Porphyrion is that it isn't viewed face-on, where we're looking down the barrel of one of these jets. Those objects are easy to see because they're so bright and are known as BL Lacerti objects or blazers. but we cannot determine how large in extent the jets from those objects are precisely because we can't view their properties in other dimensions. They're known to exist with comparable energies to Porphyrion and at even earlier times, but good measurements of them are elusive, as the jet itself outshines the galaxy. However, many of the most distant objects in the known universe, the little red dots discovered by James Webb, are so bright precisely because the light we're seeing isn't just coming from stars, but rather appears to be enhanced by black hole jets that, at least in some cases, are being beamed directly along our line of sight. In recent years, we've learned that black holes are more numerous, represent a larger mass fraction, and arose earlier and with larger masses at early times than we had previously anticipated. Now it appears we're also learning that black holes can turn on, remain active, and emit power coherently in the form of relativistic jets for much longer than we thought was theoretically possible. If this was a process that didn't just happen 7-8 billion years ago, when the universe was half its present size, but 10, 12, or 13.5 billion years ago, or back in the very early universe, then it's eminently possible that supermassive black holes are much more responsible for the shape and properties of the universe than anyone has realized up until now. But how common, truly, are systems like Porphyrion? In order to make one, you need a massive major merger that lasts for a long time and continues to feed an already supermassive black hole without disrupting it. That's a task for future astronomical surveys and will require viewing large amounts of the universe in multiple different wavelengths of radio light. With the discovery of Porphyrion, we now know which cosmic questions to ask if we want to understand the relationship between the universe's growth and evolution and the supermassive black holes and their energetic jets within it. However, the answers will have to wait until that new, yet untaken data arrives. Another remarkable pieces of news just less than a year after Japan's X-ray imaging and spectroscopy mission launched to space, the Space Telescope's first results are in, and they are stunning. The X-ray telescope, also known as XRSM, is operated by JAXA with participation from the ESA. Its first observations captured the structure, motion, and temperature of material swirling around a supermassive black hole, as well as the dynamics of supernova wreckage that marks the death of a massive star. And according to ESA XRISM project scientist Matteo Guainazzi, these new observations provide crucial information in understanding how black holes grow by capturing surrounding matter, and offer a new insight into the life and death of massive stars. They showcase the mission's exceptional capability in exploring the high-energy universe. The region around the observed supermassive black hole, located in the galaxy NGC 4151 and about 62 million light-years away from Earth, has something in common with the remains of the observed supernova called supernova N132d and located about 160,000 light-years away. They are both dominated by superheated gas called plasma. Plasma produces high-energy X-ray light, and XRism is the perfect instrument to observe that kind of light. Thus, astronomers have gained new insights into the most violent, turbulent, and powerful regions of the cosmos. XRism studied the supermassive black hole at the heart of the spiral galaxy NGC 4151 to learn about how the cosmic titan, which has a mass 30 million times greater than the Sun, consumes matter. More specifically, the spacecraft revealed details of the material that is very close to this supermassive black hole. XRISM allowed astronomers to track plasma as it circled the supermassive black hole at a distance of around 0.1 light-years away. This material gradually moved inwards to a distance of around 0.1101 light-years, about the distance between the Sun and Uranus, before falling into the black hole. Paying particular attention to the X-ray signature of iron atoms, the team was able to determine several structures around the black hole, including the accretion disk that gradually feeds it and a more distant donut-shaped torus of gas and dust. Other instruments have observed these structures in radio waves and in infrared light before, but the technique used by XRISM is the first capable of determining how plasma around a supermassive black hole is shaped and how it moves. The data could significantly assist scientists in understanding how supermassive black holes feed and grow by greedily consuming matter from their surroundings. On the other hand, the supernova wreckage N132D is much closer to home than the supermassive black hole of NGC 4151. It's located in the Milky Way's neighbor dwarf galaxy, the Large Magellanic Cloud. However, that doesn't mean the XRISM observations of this region of space are any less impressive or important. This interstellar bubble of plasma was ejected from a massive star around 3,000 years prior to the time in which XRISM sees it. Don't forget the light from this region of space has taken 160,000 years to reach us. Previously, scientists had assumed the wreckage of supernovas would expand outwards evenly in the form of a relatively simple, spherical shell of plasma. The XRISM observations of N132D, taken using its resolve instrument, seem to contradict this, with these remains shaped more like a donut. The team was also able to use XRISM data to ascertain that this material is pushing outwards at a speed of around 2.6 million miles per hour. That's about 2,000 times as fast as the top speed of a Lockheed Martin F-16 jet fighter. And that wasn't the only extreme thing about this supernova remnant. The team was able to determine that it has a temperature of 10 billion degrees Celsius. For comparison, the heart of the Sun has a temperature of just 15 million degrees Celsius. Observations like this could help scientists better understand how elements forged at the heart of massive stars are distributed through the cosmos when these stars explode. Because these elements are then integrated into the next generation of stars, this is a vital part of the cycle of stellar life and death. Since XRISM launched on 7th September 2023, its science team has been hard at work establishing the performance of its instruments and refining data analysis methods using 60 key targets. Scientists from across the globe have thus far submitted over 3,000 proposals for studies using XRISM, of which 104 have been accepted. These successful observing programs will begin next year, with these initial results indicating we haven't seen the best of XRISM yet. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. For as long as humanity has looked up at the stars, we've wondered about the origins of the universe. How did everything come into existence? For decades, the Big Bang Theory provided a satisfying answer. This powerful explosion, which took place around 13.8 billion years ago, is thought to have set in motion the expansion of the universe as we know it. But now, with the launch of James Webb, a new frontier in space exploration opened up, and with it, an unsettling glimpse into what may have occurred before the Big Bang itself. The revelations have shaken the scientific community and sparked profound existential questions about the nature of reality and the universe we inhabit. Join us as we dig deep into how James Webb just unlocked the biggest cosmic mystery. For decades, the Big Bang Theory stood as the cornerstone of cosmology, offering a comprehensible narrative of how the universe came into being. According to this theory, about 13.8 billion years ago, the universe began as a singularity, an infinitely dense point that contained all the matter and energy of what would become the universe. This state was unstable, leading to a massive expansion we call the Big Bang. Contrary to popular belief, this wasn't an explosion in space, but rather the rapid expansion of space itself. In the first tiny fraction of a second after the Big Bang, the universe was a seething hot mass of particles and energy. The four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, began to separate. This period is often referred to as cosmic inflation, where the universe expanded exponentially, smoothing out space and setting the stage for galaxies and stars to form. As the universe cooled, particles like quarks and gluons began to form protons and neutrons, which later combined to create atoms. Hydrogen and helium, the lightest elements, emerged about 300,000 years after the Big Bang during a period called recombination, when the universe became transparent to light. The leftover radiation from this event is known as the cosmic microwave background, which we can still detect today. Over the next billions of years, gravity pulled together clouds of hydrogen and helium, forming the first stars and galaxies. Inside stars, nuclear fusion created heavier elements like carbon, oxygen, and iron. When massive stars exploded in supernovae, they scattered these elements across space, seeding future generations of stars, planets, and eventually life as we know it. However, despite its widespread acceptance, the Big Bang theory has always been haunted by unresolved questions. As told, at the heart of the Big Bang theory is the concept of a singularity, a point where the laws of physics as we understand them break down. This singularity represents an infinitely small and dense state from which the universe is said to have emerged. However, the idea of a singularity itself presents profound challenges. The notion of infinite density and zero volume defies our conventional understanding of space and time, suggesting that our current physical theories, including general relativity and quantum mechanics, are incomplete. And one of the most tantalizing questions that arise from the Big Bang theory is what caused the Big Bang? What existed before it? Was there even a before, given that time and space supposedly began at that moment? While these questions have been largely theoretical, recent findings from the James Webb Space Telescope have given us new and deeply disturbing clues. Launched in December 2021, the Webb telescope has been equipped with cutting-edge infrared capabilities, allowing it to peer deeper into the cosmos than any previous telescope. Where the Hubble Space Telescope could only glimpse at faint traces of distant galaxies, James Webb can capture the earliest light emitted by the first stars and galaxies, giving us an unprecedented view into the very fabric of space-time. But Webb's capabilities extend beyond simply observing early galaxies. It can also capture data about the universe's structure, composition, and evolution in ways previously unimaginable. As scientists analyzed the data streaming in from Webb, they began to notice something peculiar, something that didn't fit within the framework of the Big Bang theory. One of the most stunning discoveries made by James Webb is its detection of structures in the early universe that should not, by all accounts, exist. Observing galaxies that are thought to have formed just a few 100 million years after the Big Bang, astronomers have encountered mature, well-organized galaxies that challenge our understanding of cosmic evolution. These galaxies seem far too old and complex for the timeline provided by the Big Bang model, which suggests that the early universe should have been a chaotic, turbulent place, with galaxies still in their infancy. What's even more alarming is Webb's observation of faint cosmic ripples, traces of energy that seem to date back to a time before the Big Bang. These ripples could be the remnants of a pre-existing universe, something that existed before the event we've come to understand as the beginning of time itself. If this is the case, it suggests that the Big Bang may not have been the true beginning, but rather a transition, a new phase in an eternal cycle of cosmic destruction and rebirth. What's notable, the idea that there might have been something before the Big Bang is not entirely new. Various theoretical models have posited the existence of a multiverse, suggesting that our universe is just one of many universes, each with its own physical laws and properties. in a vast multiverse. In this model, the Big Bang could have been the result of a local event in a larger multiverse, with other universes constantly being born through similar processes. This could involve mechanisms like eternal inflation, where different regions of space experience continuous cosmic inflation, each giving rise to a new universe. The multiverse concept offers the possibility that before the Big Bang, there were other universes or cosmic regions that existed and gave rise to our own. Another theory is the idea of a cyclic universe, where the universe goes through infinite cycles of expansion and contraction. In this model, the universe could have experienced multiple Big Bangs and Big Crunches. After expanding for billions of years, the universe could collapse back into a singularity, the Big Crunch, only for another Big Bang to occur and begin a new cycle. This concept has been explored in various forms, from ancient cosmological ideas to modern versions like conformal cyclic cosmology, proposed by physicist Roger Penrose. However, Webb's data brings a disturbing new dimension to these theories. If the faint cosmic ripples it has detected are indeed traces of a pre-Big Bang universe, then we are faced with a chilling possibility. The universe may be caught in an endless loop of destruction and renewal, where everything that exists is destined to be obliterated, only to be reborn again in a new form. This raises questions about the very nature of existence. Are we living in a universe that is fated to collapse, with all matter, life, and consciousness erased, only to be replaced by something else? The concept of eternal cycles of cosmic death and rebirth may sound philosophical, but Webb's observations lend it a disturbing degree of scientific credibility. We may be part of a universe that is not unique or special, but merely one in an infinite series, with countless others having come before and countless more to follow. The realization that our universe, and by extension, everything within it, is impermanent, subject to a cosmic reset, is nothing short of terrifying. One of the most unsettling aspects of Webb's discoveries is the suggestion that time itself may not be linear. According to our current understanding of physics, time began with the Big Bang. But if there was something before it, what does that say about the nature of time? Some theorists have begun to speculate that time might be cyclical rather than a straight line. In this scenario, the concept of before and after becomes meaningless, and the universe may be in a perpetual state of becoming, constantly evolving through an infinite loop. From the moment we are born, our understanding of reality is deeply intertwined with the flow of time. We sense its passage as a series of events, moving from the past through the present into the future. However, this perception is not necessarily an accurate representation of how the universe operates. In the early 20th century, Albert Einstein revolutionized our understanding of time with his theory of relativity. He demonstrated that time is not a constant, as Isaac Newton had previously assumed, but is flexible and relative, depending on the observer's velocity and the presence of massive objects. This discovery revealed that time and space are woven together into a four-dimensional fabric known as spacetime. This means that time does not flow uniformly for all observers. A clock on Earth, for example, runs at a slightly different rate than a clock on a satellite in orbit. The faster you travel, the slower time passes relative to someone at rest, a phenomenon known as time dilation. Yet, relativity still treats time as something that exists, even if it is flexible and malleable. More radical ideas suggest that time might not exist at all, at least not in the way we commonly experience it. In quantum mechanics, the very nature of time becomes even more puzzling. Quantum mechanics deals with the behavior of particles at the smallest scales, where the classical rules of physics break down. In this realm, particles can exist in multiple states simultaneously, and their behavior can be described only probabilistically. The concept of time in quantum mechanics is particularly problematic. At the quantum level, time often appears to be irrelevant. When physicists describe systems of particles using equations such as the Schrödinger equation, time is just another variable, treated symmetrically with space. This is in sharp contrast to our everyday experience, where time seems to move in one direction only, from past to future. In quantum mechanics, the fundamental laws of physics are time reversible, meaning that they do not distinguish between past and future. This suggests that time's arrow, the irreversible flow of time that we experience, might not be a fundamental feature of reality, but instead an emergent property. The concept of time in quantum mechanics becomes even more complicated when we consider entanglement, a phenomenon in which two or more particles become linked in such a way that the state of one particle is instantaneously correlated with the state of another, no matter how far apart they are. This spooky action at a distance, as Einstein called it, challenges our understanding of both time and space. In entangled systems, the flow of time seems to become irrelevant. The relationship between particles does not depend on a linear sequence of events, suggesting that time might be less fundamental than previously thought. One of the most intriguing theories that challenges our conventional understanding of time is the block universe theory, also known as eternalism. This idea arises from Einstein's theory of relativity and suggests that time is not something that flows, but rather a dimension in which all events, past, present, and future, coexist simultaneously. In the block universe, the passage of time is an illusion created by our limited perspective. Imagine time as a landscape. When we stand at one point on this landscape, we experience that moment as the present. However, from a higher dimensional viewpoint, the entire landscape, the past, present, and future, is laid out all at once. Just as all points in space exist simultaneously, all points in time exist simultaneously. The past is not gone, and the future is not yet to come. They are simply parts of the space-time continuum, existing as part of a larger, unchanging whole. If the block universe is correct, then time does not flow in the way we perceive it. Our experience of time might be similar to watching a movie. We see the frames one after another and perceive motion, but in reality, the entire film exists at once. Our consciousness might be moving through time in a similar way, experiencing moments sequentially, even though they all coexist in the space-time block. Despite these radical ideas about time, we still experience the world as a sequence of events. A glass shatters, but it does not spontaneously reassemble. Ice melts, but does not freeze on its own. This irreversibility of time, the so-called arrow of time, is deeply rooted in the laws of thermodynamics, particularly the second law, which states that entropy, a measure of disorder, in a closed system always increases over time. Entropy provides a direction to time that seems absent in the fundamental laws of physics. While the equations governing the universe at a microscopic level are time reversible, meaning they could work equally well if time ran backward, the second law of thermodynamics introduces a preferred direction, from lower entropy to higher entropy. This gives rise to the arrow of time that we experience. However, some physicists argue that the arrow of time may itself be an emergent phenomenon, rather than a fundamental aspect of the universe. It could arise from the initial conditions of the universe, particularly the extraordinarily low entropy state at the moment of the Big Bang. If this is the case, then the arrow of time might be a consequence of the universe's birth rather than a fundamental feature of reality. This again raises the possibility that time, as we experience it, is not fundamental, but rather a product of the specific conditions of our universe. Philosophically, the notion that time may be an illusion has profound implications for our understanding of consciousness and existence. If time does not exist as we perceive it, then what does it mean to be conscious in a world where past, present, and future are indistinguishable? Some philosophers and neuroscientists suggest that our perception of time is closely tied to the way our brains process information. The brain constructs a continuous stream of consciousness by piecing together discrete moments of sensory input, much like a film projector creates the illusion of motion by rapidly displaying still images. In this view, time may be a mental construct, a way for our brains to make sense of the universe. Just as we perceive colors that do not exist outside our minds, color is merely the brain's interpretation of different wavelengths of light, we might perceive time as a flow when it is, in fact, static. This idea is bolstered by research into altered states of consciousness, such as meditation, psychedelic experiences, and certain neurological conditions, in which individuals report a breakdown of the usual perception of time. In these states, people often describe a sense of timelessness, or the feeling that past, present, and future are all one. Such experiences suggest that our perception of time is flexible and can be altered, reinforcing the idea that time might be a mental construct. Ultimately, the question of whether time is an illusion touches on some of the deepest mysteries of existence. If time does not exist as we perceive it, then our understanding of reality, causality, and even the nature of life and death might need to be re-evaluated. Time, in this view, could be akin to a trick of the mind, a useful but ultimately flawed way of organizing our experiences. Physicists continue to wrestle with the concept of time, seeking something called a theory of everything. Some suggest that such a theory might reveal that time, as we understand it, does not exist at the most fundamental level of reality. If this is true, then the implications for our understanding of the universe and our place in it are staggering. But what exactly is a theory of everything? Well, put simply, a theory of everything would encompass all the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Today, we have two primary frameworks that describe these forces: general relativity, which accounts for gravity and large-scale structures like stars and galaxies, and quantum mechanics, which explains the behavior of particles at microscopic scales. However, these two theories are fundamentally incompatible. General relativity sees space and time as continuous, while quantum mechanics treats them as quantized and probabilistic. Bridging this gap is the central challenge for a theory of everything. Albert Einstein's general theory of relativity, formulated in 1915, revolutionized our understanding of gravity. In Einstein's view, gravity is not a force in the traditional sense, but rather a consequence of the curvature of space-time. Massive objects like stars and planets warp the fabric of space-time, causing other objects to move in response to that curvature. This insight replaced the Newtonian idea of gravity as a force acting at a distance and explained a variety of phenomena that Newtonian mechanics could not, such as the precise orbit of Mercury and the bending of light around massive objects, gravitational lensing. General relativity has been incredibly successful in describing large-scale phenomena, such as the dynamics of galaxies and the expansion of the universe. However, it breaks down at extremely small scales, particularly in describing the center of black holes or the conditions of the universe just after the Big Bang. At these scales, quantum effects become significant, and general relativity alone cannot provide a complete picture. Quantum mechanics, developed in the early 20th century by scientists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, provides a detailed description of the interactions between subatomic particles. Unlike general relativity, quantum mechanics deals with probabilities rather than certainties. The behavior of particles is governed by wave functions, which describe the probability of finding a particle in a particular state. This probabilistic nature is fundamentally different from the deterministic view of space-time in general relativity. One of the triumphs of quantum mechanics is the standard model of particle physics, which unifies three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. The Standard Model successfully describes a wide range of particle interactions and has been confirmed through countless experiments. However, it does not include gravity, the fourth fundamental force, nor does it explain certain cosmological mysteries, such as dark matter and dark energy. The biggest obstacle to a theory of everything is gravity. While general relativity beautifully explains gravity at large scales, it doesn't work at quantum scales. When physicists try to apply quantum mechanics to gravitational fields, they encounter infinities, mathematical quantities that make no physical sense. This issue becomes especially critical in extreme environments, such as black holes, where both quantum effects and gravitational effects are significant. The mathematical incompatibility of gravity and quantum mechanics suggests that we are missing a deeper theory that can unify them. Physicists believe that gravity must have a quantum description, but no one has yet found a consistent theory that works in all situations. This has led to the search for new ideas, such as quantum gravity, which could unify general relativity and quantum mechanics under one framework. One of the most prominent attempts to develop a theory of everything is string theory. In string theory, the fundamental building blocks of the universe are not point particles, as in the Standard Model, but rather tiny, vibrating strings. These strings can vibrate in different ways, and the different patterns of vibration correspond to different particles. In this framework, gravity emerges naturally as one of the vibrational modes of the strings, thereby incorporating gravity into a quantum framework. String theory also introduces the concept of extra dimensions. While we are familiar with 3 dimensions of space and 1 dimension of time, string theory suggests that there may be additional hidden dimensions that are compactified, curled up so small that they are imperceptible to us. These extra dimensions could help explain why gravity is so much weaker than the other fundamental forces, as it may be spread out over these additional dimensions. However, string theory is far from proven. One of its major criticisms is that it is not experimentally testable in any practical sense. The energy scales required to probe the structure of strings are so high that they are beyond the reach of current or foreseeable technology. This has led some physicists to question whether string theory is truly a scientific theory, as it currently lacks the ability to make falsifiable predictions. Another approach to unifying gravity and quantum mechanics is loop quantum gravity. Unlike string theory, which attempts to replace point particles with strings, loop quantum gravity works directly with the fabric of spacetime itself. It proposes that spacetime is quantized at the smallest scales, forming a network of discrete loops. These loops form a kind of atomic structure of space, similar to how matter is made up of atoms. Loop quantum gravity has had some success in explaining certain phenomena, such as the behavior of black holes and the Big Bang. However, like string theory, it is not yet complete, and much work remains to be done before it can be considered a viable theory of everything. Any theory of everything must also account for 2 of the biggest mysteries in modern cosmology: dark matter and dark energy. Dark matter is one of the most critical ingredients in the universe, but it's something we cannot directly observe. It doesn't emit, absorb, or reflect light, which makes it invisible to telescopes. Instead, its presence is inferred through its gravitational effects on visible matter, such as galaxies and galaxy clusters. Without dark matter, many of the structures we see in the universe today, from galaxies to massive clusters of galaxies, would not have formed. The first hint of dark matter's existence came in the 1930s when Swiss astronomer Fritz Zwicky observed the Coma cluster, a collection of galaxies. Zwicky noticed that the galaxies in the cluster were moving much faster than expected based on the visible matter alone. To account for this discrepancy, he proposed the existence of missing mass, what we now refer to as dark matter. Further evidence came in the 1970s when astronomer Vera Rubin studied the rotation curves of spiral galaxies. Rubin found that stars at the outer edges of galaxies were moving just as fast as stars closer to the center, a puzzling result because, according to Newtonian mechanics, the stars on the outskirts should be moving slower if only visible matter was present. The explanation for this anomaly was that an unseen mass, dark matter, was providing the necessary gravitational pull to keep those stars moving at such high speeds. While dark matter has been established as a critical player in the universe's evolution, its composition remains a mystery. One prevailing theory suggests that dark matter is made of WIMPs, for weakly interacting massive particles. These hypothetical particles would interact with regular matter only through gravity and the weak nuclear force, making them difficult to detect. Despite several experiments designed to catch a glimpse of WIMPs, including underground detectors and particle accelerators like the Large Hadron Collider, LHC, none have yet provided definitive evidence. Another theory posits that dark matter could be composed of axions, ultralight particles that might also interact weakly with ordinary matter. Like WIMPs, axions have eluded detection, but ongoing experiments continue to search for them. There are also alternative explanations for dark matter's gravitational effects. Modified Newtonian dynamics, also known as MOND, is a theory that suggests the laws of gravity might need to be tweaked to explain galaxy rotation curves without invoking dark matter. However, MOND struggles to explain the full range of cosmological observations, such as the cosmic microwave background and the formation of large-scale structures in the universe, where dark matter plays a central role. Despite its invisibility, dark matter is essential to the universe's structure. It acts like an invisible scaffolding upon which galaxies form and grow. Without dark matter, the early universe's matter density wouldn't have been enough to pull together into galaxies and clusters through gravity alone. Furthermore, dark matter's gravitational effects are critical in the study of cosmic phenomena, like gravitational lensing, where massive objects bend light from distant sources. Observing these light-bending effects allows astronomers to map out where dark matter is located, even though it remains unseen. While dark matter explains the gravitational forces holding galaxies together, dark energy addresses a completely different mystery: the accelerating expansion of the universe. Rate. In the 1990s, two independent teams of astronomers were studying distant supernovae to measure the universe's expansion rate. They expected to find that the expansion was slowing down, as gravity from matter should be pulling everything back together. Instead, they found the opposite. The universe's expansion was accelerating. This was a shocking discovery, as it implied the existence of a new, unseen force that was pushing galaxies apart. To explain this unexpected acceleration, cosmologists introduced the concept of dark energy. However, dark energy is even more elusive than dark matter, and its nature remains largely speculative. One leading hypothesis is that dark energy is related to the cosmological constant, first introduced by Albert Einstein. In his theory of general relativity, Einstein included a term called the cosmological constant, which acted as a repulsive force to counteract gravity and keep the universe static. After Edwin Hubble's discovery of the expanding universe, Einstein abandoned the idea, calling it his greatest blunder. However, the discovery of the accelerating universe brought the cosmological constant back into play as a potential explanation for dark energy. In this context, dark energy could be thought of as a property of space itself. As space expands, the energy density associated with dark energy remains constant, leading to the universe's accelerated expansion. This model fits current observations well, but it leaves many questions unanswered. For example, why does dark energy have the value it does? If the cosmological constant were slightly different, the universe might have expanded too rapidly for galaxies to form, or it might have collapsed in on itself. Another possibility is that dark energy is related to a dynamic field known as quintessence, which evolves over time. Unlike the cosmological constant, quintessence would change its strength as the universe expands, potentially providing a more flexible explanation for dark energy's effects. Dark energy is the dominant component of the universe, making up about 68% of its total energy density. Its influence has become more significant over time as the universe expanded. In the early universe, dark matter and radiation played a more prominent role, but as space grew larger, dark energy began to dominate, driving the accelerating expansion we see today. Dark energy has profound implications for the universe's fate. If the acceleration continues indefinitely, the universe will keep expanding, causing galaxies to drift farther apart. Eventually, distant galaxies may become so far removed that their light can no longer reach us, plunging the universe into a big freeze where stars burn out, and all that remains are isolated black holes and cold remnants of once luminous galaxies. Put simply, together, dark matter and dark energy make up about 95% of the universe's total content, but we know very little about their true nature. Neither dark matter nor dark energy is explained by the Standard Model or by general relativity, which suggests that our current understanding of the universe is incomplete. A true theory of everything must not only unify gravity with quantum mechanics, but also explain the existence and behavior of dark matter and dark energy. Thus, despite the progress made in theoretical physics over the past century, the quest for a theory of everything remains unfinished. Some physicists believe that new experimental discoveries, perhaps from high-energy particle colliders or precision measurements of cosmological phenomena, will provide the missing pieces of the puzzle. Others suggest that the very framework of physics may need to be radically rethought, requiring new concepts that go beyond space, time, and matter as we currently understand them. In the end, whether or not such a theory will ever be found remains an open question, but the pursuit itself has already deepened our understanding of the universe and our place within it. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.